A very warm morning and welcome to day 2 of GIAN course titled Renewable Carbon and Fuel from Organic Waste at Central University of Rajasthan. After an insightful and engaging first day filled with stimulating discussions and knowledge sharing, we are all set to continue our journey into the depths of the theme today. Without further ado, let's commence day 2 of with our first session. The speaker for today's session is Dr. Pramod N. Kamble, Associate Professor, Central University of Rajasthan. With nearly 30 publications, he has made significant contributions to environmental research. He has also led impactful projects including development of an institutional herbal garden at Central University of Rajasthan, funded by the National Medicinal Plants Board, New Delhi, Ministry of Ayush, Government of India. His research interests include soil and water chemistry, bioremediation, air, water, and soil pollution mitigation, as well as water pollution mitigation using phycoremediation. I invite Professor Kamble to deliver his lecture.
Am I audible? Yes, am I audible? Okay. So, very good morning to all. So, indeed, it is a great pleasure for me to be part of this global initiative of Academic Network GIAN program. And I am very much thankful to coordinator of this program, Bhagwan sir, and Dean of School, Devesh Sharma sir. And since yesterday we have been listening to the very renowned personality in the field of solid waste management, that is Professor Sandeep from USA, and he has given overview of all kind of biomass and the carbon sequestration potential. He has talked about chemistry and whatever the things that need to be disseminate, all kind of things he has explained very nicely. So today I am going to deliver a talk on very important subject, that is role of plant biomass in enhancing soil fertility and advancing sustainable carbon management. And everyone is talking about providing energy to vehicles or maybe to run machinery, but I would rather focus on providing energy to living organisms, and that is through carbon cycling or nutrient cycling. Okay. So let me begin with introduction. So if we take the example of plant biomass, right? So how does it, there are very first question, that is how does plant biomass contribute to soil fertility, right? So simply, if you look at the current situation of the soil ecosystem, it's very deteriorating, and for that largely anthropogenic activities are responsible, and more precisely the climate change is largely responsible. So we need to think about how to regenerate that soil, and that is where the main focus of the people lies on the sustainable agriculture practices. And then second question one should ask, how we can include plant biomass into management, sustainable management of carbon. And we do know that plant biomass, through various processes like decomposition, then cycling, and then it's basically incorporating into soil, and ultimately it plays a very important role in maintaining the soil health and promoting the carbon sequestration. So these are the some of the processes that is happening in soil ecosystem. So plant growth is basically, it is a very natural process. If you look at the carbon sequestration potential of plant is very high, and because of that everyone is talking about the cultivation or development of vegetation cover area. So if you look at the plant growth, so plant do absorb CO2 and it convert into organic material through photosynthesis. That means light energy is converted into chemical energy. This is the normal ecological process, and since I think school days we are listening this particular term. But however, we are not understanding how this particular mechanism can be utilized in order to restore the degraded ecosystem. And then impact of that particular plant growth and sequestration of carbon is it promoting microbial activity, providing carbon to the soil ecosystem. And then finally carbon is stored in large amount, even though atmospheric carbon can be sequestered by the plants. The next is decomposition. Decomposition process is very like one of the very important process which is happening in environment, and it is basically initiate the cycling of the all kind of the nutrient including carbon, nitrogen and phosphorus. And I would say decomposition process is one of the key process which very much required in order to maintain the cycling mechanism of the ecosystem. Then soil incorporation, like root biomass, like rhizosphere activities are there, and in rhizosphere, if you look at the rhizosphere, it is one of the active zone. So you will see that the supply of carbon is there, and in that carbon is very significantly utilized by the microorganism fungi, and they do mineralize that particular organic matter very significantly, and they do release certain kind of the nutrient which are very essential for the plant growth. And whenever you think about rhizosphere, so that time you have to focus on microbial activity. The next is formation of humus. So in case of humus, we have to take example of primary succession. So primary succession is the best example of the humus development. So initial stages, there some kind of the plants like lichens, mosses, they do provide conducive atmosphere for the development of the soil structure. And initially the development of humus layer occurs there, and then it begins like development of life is taking place at any place of the world or globe. Then soil microbial activity. So already I did mention the microorganisms are one of the very important agent in the ecosystem, and they do mineralize the all kind of organic matter or decomposable material, and they provide or supply these nutrients to each and every living organism. Those are present in ecosystem. Then what is plant biomass? So normally we do talk about plant biomass is like total mass of the living plants in a given area. Sometimes we consider dry mass also biomass of that particular plant. But again it is divided into two parts, maybe like above ground biomass and another is the below ground biomass. So above ground biomass includes leaves and stems, and below ground biomass include roots. And there are certain kind of the sources of biomass that are basically I would say this is a universal truth that these kind of the sources are providing ample amount of the supply of the biomass. For example, agriculture sector providing the agriculture residue, then forest residue where it includes branches and foliage, then cover crops and weeds also the best source of the biomass. If you look at the life cycle of the weeds, so if you go to the field, you will understand that initially in rainy season it grows, and then ultimately in case of in summer season when they are dying, that time they are providing biomass to the soil ecosystem, and this is how this cycling of the biomass incorporation is taking place. So we have to understand these ecological processes in order to use that plant biomass for further improvement of the soil ecosystem. Then these are the some of the sources of agriculture waste, like crop residue. It includes rice straw, wheat straw, corn straw, barley straw. Then livestock waste like cattle manure, poultry waste, soil manure, animal fat. Then agro-industrial waste, sugarcane bagasse, rice barn and husk, de-oiled seed cakes, fruit peels and pulp. De-oiled seed cakes, like if you look at the traditional mechanism, where in like most of the Indian people used to produce oil, edible oil on their own, and this particular oil seed used to produce cakes of that residue, and that residue is used to, like, people used to use that residue for feeding the cattle, and then sometimes they used to send that particular waste to the soil ecosystem in order to maintain the soil fertility. Then fruit peels and pulp. Then aquaculture, it includes metabolic waste, fish waste and seaweed and algae. So these are some of the very important sources of the biomass which is being provided by the agriculture sector. Then summary of availability of the agriculture waste in India and production. So annual crop residue around 500 million tons that is being produced in our country. Then surplus residue 140 metric tons, that is million ton is being produced, and it is like around 92 million tons waste is being burned without considering its importance. So that particular burning is very, like, creating huge amount of problem. Like for example, it is giving rise to emission of the greenhouse gases into the atmosphere, and very significantly pollution level are increasing. So if we take the example of Delhi pollution levels, the main cause of the pollution, air pollution of Delhi area, it is the burning of plant residue. So from Haryana and Punjab people, they are basically burning the residue, surplus residue. It is having, so like economic loss of around 92,000 crore rupees. Then role of plant biomass in enhancing the soil fertility. So improvement of soil structure, that is we do know. So when you look at the root, basically root promotes the root development itself and also provides way for the water infiltration, and by doing so it maintains both supply of the nutrient and cycling of the other component. Those are essential for the growth of the plant. Then nutrient cycling, so mineralization of the biomass is being happen through, so decomposers, bacteria and fungi are responsible for that, and the mineralization of nutrients like nitrogen, phosphorus and potassium happens very nicely, and they send back to soil again, and that, so nutrients are again being utilized by the plants and living organisms, those are present in the ecosystem. And then ultimately it is basically increases the soil organic matter. So soil organic matter, we do know the role of soil organic matter. Soil organic matter plays a very crucial role in order to maintain the various kind of the balance, for example cation exchange capacity. So CEC is one of the very important parameter which maintain the buffering mechanism in soil ecosystem, and through this the supply of nutrient is taking place in a conducive manner. Then biomass decomposition and carbon sequestration. So biomass is decaying, biomass is one of the way to store carbon into the atmosphere. Okay, and then if you look at the plants, sorry. Okay, sorry. So plant basically absorbed CO2 and through root zone, say atmospheric CO2 being absorbed by the plant, and when it thing comes to the rhizosphere, again that CO2 is being released by the carbon through root zone. So root exudates are the main source of the organic carbon into the soil. So might be many of you know that, like many people are come from the microbiology background, so they do know how this particular mechanism of soil carbon sequestration is taking place through plant itself. Then carbon sequestration, it is simply the biomass is basically main source of the carbon sequestration. So how to quantify that? So whenever the growth of biomass occurs, that indicates the potential of the carbon sequestration. And there are two kinds of the carbon sequestration that are happening. So one is the short-term carbon sequestration. So if you look at the agriculture sector, it is the best example of the short biomass sequestration or carbon sequestration. So initially what we do add carbon into the soil, then we grow plants and that we harvest that particular plants, and it is a kind of seasonal sequestration or temporary sequestration of carbon is taking place. And long term basically, so that already did mention the humus development. The best example is primary and secondary succession in the ecosystem. These are the some of the ways of carbon sequestration. The next, biomass and sustainable carbon management. So very significantly we can reduce gas emission through sequestration of the carbon, right? But we are talking about converting biomass into usable form of energy, but still during conversion of such kind of the mechanism, we are producing certain kind of the gases or polluting the environment. But however, if we really would like to conserve our environment, we have to cycle that carbon, and cycling process is there. It is ecological process, and the plantation could be the best way to the sequestration the carbon, right? The most of the people are not at all understanding the importance of this particular plantation mechanism. And right now, but however, United Nations organization like United Nations and many other organizations are looking for that, and they are providing conducive atmosphere for the plantation and providing huge amount of funding for the plantation. The next is biochar production. So biochar, like everyone is talking about biochar, we are burning the biomass through pyrolysis, and during that process also some amount of gases or some amount of pollutants are being emitted, and again we are responsible for into the atmosphere. Biochar, but it is having a very significant value in case of the maintaining the fertility of soil. So if you add biochar into the soil ecosystem, very significantly it do absorb the nitrogen, phosphorus, and the slow supply of nitrogen, phosphorus is taking place, and whatever carbon present in that biochar, it is being utilized by the microorganism in order to recycle or mineralize that particular nutrient. And this is how the nutrient balance and cycling and supplying is taking place in this soil ecosystem. Carbon farming practices. So carbon farming practices is one of the very essential tasks, and we call it as a organic farming. And most of the people of like country like India, they are following this kind of the mechanism in order to increase the agriculture productivity. But however, what kind of initiative has been taken by the government authorities? So government authorities are providing huge amount of funding to some kind of the farmers, and like recently in budget they have sanctioned huge amount of money in order to implement organic farming mechanism. And why we need to think about organic farming? Because in near future, like if you take the example of current scenario of the health of the human being, and so many people are affected by the disease like cancer, and the major cause of cancer is a soil pollution. So we are adding various kind of the chemicals into that, like pesticide, insecticide, chemical fertilizers, and because of that these chemicals are responsible like creating harmful impact on the health of the human being. Okay, so in order to avoid this kind of the problem, we have to focus on organic farming, and that's what government is doing. Then why soil ecology? Why we have to think about soil ecology? So simply many people say that कि क्या soil में काम करना है, ऐसे ही करते हैं, right? But soil is one of the very important natural resource. Without that resource, we cannot able to survive on living planet Earth. So importantly, at very beginning I did mention about, I am going to talk about energy supply to the survival of living organisms. Okay, so in 21st century, the human beings, or not only human being, rather all living organisms are totally depends upon the soil products, and whatever may be food that is developing or we are growing, it is come from the soil ecosystem. And important thing why we need to think about soil, that is it provides like act as a pool of biodiversity, and it provides opportunity to study the phenomena of the biological diversity. Then it is also excellent place to study ecology, and whatever the conservation mechanism that you would like to implement, like all ecological processes are happening in soil ecosystem. If you understand the ecological processes, you will very nicely you can implement the conservation mechanism. And most of the government agencies would like to have consultancy in order to implement their policies. So those people are working in this particular field, they have to understand the soil ecological processes, and so that they can disseminate their knowledge to the government agencies, and very nicely government agency can make use of that kind of the study, and they can implement the conservation mechanism of the soil. Then degradation of soil, like there are many causes of the degradation of soil. So deforestation is one of them, improper agriculture practices, mining activity, widespread pollution, and inclusion or development of invasive species. Then also extra pressure of population is being created. So we do know the, like if you take the example of carrying capacity of the earth, it is 3.5 billion people can be sustained on the earth living planet, and that is the that much amount of resources are available, like taken in log C and no addition. C is a carbon addition and no is a control. So always it is resulted into higher growth. So its extent of C limitation is very evident here with respect to the nitrogen. Conclusion for study, soil vector limited by the carbon. Then extent of carbon limitation increase with the increasing N status of the soil. And then control soil almost carbon and nitrogen limitation simultaneously, and the same result were found in mineral and organic soil. Then second very important study that we have done, that is induced N limitation and effect of carbon loading on the bacterial growth. So we are talking about the addition of carbon, right, and we are like basically looking for carbon sequestration, right. So in case of India, we are using 250 kilogram of urea fertilizer for a hectare, and it is huge amount of fertilizer we are adding, and because of that it is creating toxic impact on the microbial activity, right. So that particular part, how to reduce that particular problem or how to mitigate that problem. So if you think about the carbon load, so carbon can be very play very important role in case of the mitigation of this kind of the problem. So we found out FIBA, so we can add carbon rich substrate into the soil ecosystem. Definitely we are going to have certain kind of the change. So this model is very well known, like since this is not a new thing, because traditionally we are practicing all kind of the mechanism, but theoretically we prove this part 40 milligram per gram of soil. So if you look at the straw it is having a 75 CN ratio. Then starch is a pure sugar. It is a pure sugar, so it is full of carbon and glucose. So and then we after treatment we sampled these samples for 1, 2, 3 and 7 weeks, and in case of starch it is 2, 3, 4 and 7 weeks. So and after that we added carbon and nitrogen into the soil sample, and we studied after 72 hours of incubation we estimated the bacterial growth using the leucine incorporation. So direct effect of starch, additional bacterial growth. So in every soil the straw and starch has shown higher growth as compared to the control after addition of the starch and straw. Then measurement of bacterial growth is being used by this particular addition, like we already optimized concentration were used to look at. So if you look at this particular figure, and different rates of this particular concentration of the starch. So, weeks of the treatment, you can see the bacterial was switched from being C limited to N limited, and this is like the cycling mechanism occurs in a natural cycling mechanism occurs in the ecosystem, right? So whenever you come across such kind of the problem pollution, that time we have to focus on the carbon. So carbon is very important agent, plays very important role in maintaining the growth mechanism of the living organism. Even we people do require carbon. So ultimate, like if you look at the metabolic activity, glycolysis pathway, it like develops like last product byproduct of the metabolic activity is what? Liquid glucose, and it is being stored in the liver itself. So similarly, bacteria, other living organisms, they do require to have a supply of the carbon, okay, and we have to maintain this particular structure, and this is what we call as a carbon sequestration. But sequestration is a different thing. So sequestration, you cannot keep carbon like that, right? So we need to circulate that carbon. So one thing you should understand regarding the ecosystem services, whatever you do, even if you producing polluting agent, we need to know how to cycle that particular chemicals or pollutant into the environment, and that is the ultimate solution. When like we don't have any kind of the concrete solution for pollution, but if you know the how to cycle that particular, even plastic or whatever may be like byproducts of human activities are there, to cycle them according to the ecosystem, and then only we can have a solution to that particular problem. That is what done in our study. So same thing happens with straw addition, but straw has shown higher like impact after 4 weeks of the treatment as compared to the starch, and it has been observed that the straw addition was like favoring bacterial growth, sorry, fungal growth, and starch will favor bacterial growth. So simplified way to look at how this mechanism happens here. If you look at this, we have taken CN ratio, log ratio of CN addition, and if it is like more than 0 indicates the C limitation, and 0 limitation. That means we have able to convert soil from being C limited to N limited, addition of the substrate. And same thing for the addition. So conclusion, starch and straw addition into bacterial indicates initial C limited conditions. Then amount of straw and starch resulted in higher bacterial growth, that like direct effect of straw and starch addition. Then inhibition of starch and straw switched to bacteria from being limited to be N limited, and N limitation was more evident in the control soil with the lowest N status. Then comparison of fungal growth and like growth after elevating the induced N limitation. So we have used same concentration of the nutrients. Then if you look at the comparison, so fungal growth also switched from being C limited to N limited. Then fungal growth and respiration. So we compare respiration irrespective of the addition. It has shown some kind of the different result, but respiration is not reliable method to find out the exact limiting factor for the bacterial growth or fungal growth, because waste metabolism can be occurred, but there are many biological microbial agents are there in the soil, and to that diversity we cannot rely upon the respiration technique in order to find out the exact limiting factor for the bacteria. Then particular study is after 4 weeks of straw and starch and fungal were switched from being C limited to being N limited. Then bacterial growth, fungal biomass, fungal growth and respiration, similar results. Then however, N limitation starch promoted mainly bacterial growth, and while as I mentioned, while in straw millet soils, fungi responded most after adding in, because fungi do love cellulosic material and huge amount of cellulosic material is available in straw, and that cellulosic material is being utilized by the fungi in order to mineralize the nutrient. Then last part, we studied soils from the India, which is having high pH and high salinity. So how much time do you have? So we studied the nutrient limitation for bacterial growth, then bacterial community response to pH, bacterial community tolerance to the NaCl, effect of substrate, alpha-alpha straw starch on bacterial growth, and microbial community structure. Then PLFA pattern that we have studied. So we done the principal component analysis, and we have found out that close relationship between saline soils like 5, 6 and 12 number soil were shown the same kind of the results. And here if you look at the blue square indicate the PLFA indicatives for fungi, the soil 6 relatively high in fungi and soil 3, 10 relatively low. So it indicates the bacteria itself. So after addition of straw, very nicely the fungal growth is occurring, but like agriculture soil, it is not evident that the fungal growing is like that, because in agriculture field bacteria is dominating, and in forest ecosystem fungi is dominating. But after addition of straw, we have seen the growth of the fungi as well. Then this is the effect of substrate amendment on soils. So 12 soils to like from the India, and it was like basically similar results. So primary limiting factor for bacterial growth was carbon, and secondary was nitrogen. So then again the different kind of the impact of straw addition, how it is happening, like fungal growth, then in case of respiration, in case of bacterial growth, having a different kind of structure, like starch and straw had a very nice impact on growth. Then again the conversion of bacterial community from one limitation to another limitation. So bacterial community respond to the, so we use different kind of the buffers from 2, 4, 6, 9, and then we found out the optimum pH for bacterial growth was equal to the soil pH. That means the bacterial community is adapting to the extreme conditions. Then we studied the salt tolerance, like if you look at the soil 5, soil 6 and soil 12 have shown higher inhibiting concentration as compared to the other soil. Again, it is evident that the extreme environment, like many bacteria can adapt themselves. For example, Bacillus sporifera, Pseudomonas fortida and Halomonas bacteria are some of the bacteria, they are showing tolerance to the salt. But however, in this study, we are not focused on particular bacteria, we are dealing with the bacterial community as a whole. So this is again comparison between IC50 values and the conductivity. Increasing salinity has shown increase in IC50 values. So we compared our PLFA pattern for high pH with who's pulled soil from London, and we found out some results. Okay, so already I have explained everything, which is like most important result that already I have explained very nicely. Okay, thank you very much. Yes, any questions?
Any questions? But before the tea break, it's time for felicitation of our distinguished speaker, Pramod Kamble sir. So I request Dr. Vibhuti Bhushan Sahu from Vellore Institute of Technology, Tamil Nadu, to kindly felicitate Pramod sir. Thank you, sir. We will have a short tea break in some time. Meanwhile, you can have interaction with our professors, and if you want to ask or discuss any topic, you may. The floor is open for discussions. Please put forth your thoughts and your questions, queries.
Anyone? Expectation from the course, you want me to cover something which unknowingly I'm not discussing there, or you want me to discuss something of your interest? Yeah, whatever. Yeah, it's a networking program. So let me tell you, renewable carbon is the topic, it's a theme, but it's a global initiative of academic networking, which you are building network. Our idea is to make you grow academically in your career, whether you stay in India, you go abroad, or wherever, but knowledge is the best. So how we can share and how we network. Anyone? Okay, let me ask you. How many of you want to go for higher studies? You already PhD, so higher study would be postdoc or something else. Am I right? How many are MSc? Okay. So tell me, one by one, where you want to go for postdoc?
So, like I'm working under the supervision of Dr. Bhagwan only. So currently I'm working on extraction of pectin from agricultural waste. So like in my previous semester I did with orange peels and stuff. This time I'm doing with different stuff, which is like I'm currently working on it only. So I would like to pursue that only, and I would like to broaden my field than just agricultural waste and not just pectin but other materials as well.
Yeah, that's good. So what kind of solvent you are using?
Currently I'm using ethanol for coagulation, and like I have done with acidic extraction as well, and as well with some green solvents also I have used for extraction. So
yeah, that's very good idea, because agriculture waste is kind of feedstock and you can make many things out of it. So I was discussing extractive, and there are many high value compounds you can get out. So if you go green and economical process, it's a very good potential. I think if you are getting good result, it's a startup idea also. All right. Don't be shy, be ambitious and bold, and I think it should work. Okay. Anyone else?
So yesterday we were talking about modifying the charcoal or modifying the biochar. So can you highlight non-synthetic ways of modification, because mostly acids are used for the activation of the biomass and then it is pyrolyzed for making of the biochar. So how do we like? Are there any? Is there any way which is non-synthetic? Like if like it's a very good filter as well. The charcoal, activated charcoal, it's a very good filter. So if like this idea could also be implemented in villages and around na, if we have a non-synthetic way.
So, non-synthetic means
Not using acid or something, like
Yeah,
something
yeah.
that is available to them as well.
yeah. So I'll tell you maybe in biochar topic when we are discussing.
Yes.
I have one case study. We did a project for EPA, Environmental Protection Agency, and we tried to use biochar for lead removal. So there is a context to it. There is a city in United States in Mississippi. They had water issues one time, failure of a treatment system, so high amount of lead was coming. Okay, so it was kind of emergency situation. You don't want to allow lead in drinking water for a long time. Treatment system, how soon they can bring it. And at the same time for drinking, they were bringing truckloads of water bottles to distribute. And that's not sustainable. Means you can do 1 or day, 2 days, but not, and you are creating plastic waste parallelly. So one of them contacted me that you are working in biochar, do you have some ideas about this, what we can do? So since it's an emergency situation, it's a public health issue and all, I didn't jump on it because you need to be fully tested, proven, then recommend. But that idea gave me that there's a potential to go in that direction. Okay, so what we did that we developed a tabletop biochar maker. I will show you later. So for filter, you don't need whole lot of biochar. Am I right? If you are using for land application, you need tons of biochar and acres of land and hectares of land. But for a water filter application, you just little bit, a pound.
Like we can use other materials along with that.
Yeah.
So that absorption is also.
Yeah, so you need maybe pound, a kg or something like, not more than that. So we showed that you can make biochar using your tin cans and other thing, pyrolyzer, and that biochar we tested and it removes almost all lead immediately. Within 30 minutes you will see 100% removal for lead. So that showed potential, and that's where the engineering side comes up, how you make it like a product now which public can use. In lab we do so many things, it shows potential. Okay, now the next step comes is translation. How you translate this data that a product like a filter anyone can use it. And that was the concept. We showed that, we tried to make it, and I'll discuss what issues we faced when developing as a product. Because cost is very low. We didn't buy anything. You have a yard waste in your anywhere, collect it, make pyrolyzer, make your own pyrolyzer. But now this biochar, how you turn into a filter, which you know how long to use and make sure nothing coming out and all. So I'll discuss those issues, and that's where we need a better idea, translation idea. Okay, and that's natural, non-synthetic there, am I right? Just make biochar, and maybe your steam treatment is also not chemical, am I right? It's, you can say it's non-synthetic itself.
Also requires a closed environment, right?
Yeah.
We cannot do it in an open environment.
Yeah, so you can think of means.
And if we talk about rural areas, the resources there are very limited. So there should be a method now, so they can develop the biochar itself and implement it.
Yes, so that was the idea. You make your own biochar. That was our own theme. Okay, and the price point we kept it less than $1. So less than $1 may be costly here, but in US it was cheaper. All right, so that's the theme we brought it, and someone has to take from there. We are mostly in academics, so that's why I said a startup idea here. If you can turn into a filters, it's a social impact. Okay. Anyone else? Thank you. That's a good question. Yes, ma'am. You are going for a postdoc? So what area you work?
Sir, I did in my PhD electrochemical oxidation processes.
Electrochemical oxidation,
Yes,
okay.
yesterday I talked some of the materials also, like electrode material. I'm mainly focused on sustainable electrodes like carbon, and I have enhanced its efficiency by using scrap carbon ion fillings, which is a scrap from
Metal
steel.
industry, yeah.
It's from steel industry.
Yes.
I chipped it down and at nanoscale and used as a catalyst to enhance the efficiency of the electrochemical cell. But the problem is that it itself become a waste. So, is there any scope in your lab that we can do some kind of coating or do,
Coating, what kind of coating? Yeah, we
yeah,
can.
for
Not in my lab, but my university, there are a lot of chemistry department, materials department, and I know most of them. So if you can go specific what coating and all, definitely I can help you.
okay.
And I can connect you with them, or I can be coordinator on both sides.
And sir,
So-
what about in your lab?
My lab is not coating, but it does all the activation. Electrochemical we are doing, we have potential state, and we are looking at electrochemical reduction.
Okay.
Oxidation also we have started doing for wastewater.
Yes, sir. I did also. I did for anti-cancer drugs. I did oxidation for that.
So I will show you one project if I get time here. What we are doing that we are taking wastewater. Still
Yes,
a
sir.
start of the projects. We don't have much data, but it's funded.
Okay, sir.
So our idea is take wastewater, do oxidation, make most of the carbon go in CO2, okay, dissolved organic carbon, COD or what you say. Now once you get that COD out in the form of CO2, now we are putting reduction side
Okay.
immediately. The other cell will do a reduction, so electrochemical reduction, and then we are trying to make methanol out of it, methanol or ethanol. Okay, so entire integrated process looks like more sustainable, means from wastewater we're making ethanol or methanol, or wastewater treatment, if you look at closely, they use methanol in
Okay,
wastewater treatment to feed organisms. So that's the concept we propose. So definitely email me, okay, even if cannot now, then in future something comes up, we'll connect.
Okay.
Okay, coming to that,
Coating material. So you are working with waste iron, right? So that iron can be coated with the titanium, so that your material electrode which you are planning to use, that will sustain for longer duration and it will become as a stable electrode.
Yes, sir. And it will enhance its oxidation reduction potential
Exactly,
also
exactly.
to enhance
So
the
coating
radicals.
of titanium on this iron material which you are planning nanomaterial. So if you coat it molten state, then it will become as a solid electrode which will be stable for electro oxidation, as well as you can utilize for electro chemical reactions where electroflotation or electro oxidation is going to have a higher rate. So that way you can have coating and then you can use it.
Sir, I plan to coat the material on graphite electrode only because to scale up further the process, the
Yeah,
titanium.
graphite
Yes, sir.
itself, it is a stable electrode.
But sir, it gets abraded during the process.
So under such condition, you need to like combine with the diamond materials.
But sir,
In
it's,
case of graphite,
yes.
because that will become stable. So that will initial cost will be higher, but the processing cost will get reduced. Means your electrode is not going to get sacrificed. It will stay for longer duration. But initial cost will be higher when you combine this graphite with diamond. Capital cost will be higher.
Yes, sir.
So that is one of the way where we can extend the life of stability of the electrode.
Thank you, sir.
so I'll suggest you stay connected and we'll find out where you can do. There may be. I will go one more topic. Many of you I saw that looking for postdoc, okay, and you want to do that. I will say how to look for postdoc, okay. For in my lab, right now I don't have funding to support a postdoc, but keep getting funding time to time. So if I have something come up and we are connected, definitely, normally I go to LinkedIn or other places, I post it. So that's the one way. But in general, when you are looking for postdoc, we start writing. We know this professor we write, we know this. But the timing has to be right, okay? I want to fund you as a postdoc, and right now I don't have a project. So liking is not going to help, am I right? Postdoc budget is in US is about $100,000 per year, dollar per year. $90,000 to $100,000 per year. If I have budget, then we will be able to fund you $50,000 to $60,000 per year, your salary, all right? Because the rest of $30,000 to $40,000 goes for benefits, insurance, and many other things, indirect cost. So if you are writing to a professor and if he does not have a project of that size, then he may not reply you and your email goes in blank. And if he'll like have time or think that, he may reply you like me what I'm saying. It's not, and I'll do that. Okay. So the homework for looking for postdoc is look for faculty. Let's say you choose 10 faculty, 10 institution. Then look for their projects, what they are doing. And these are all public data. You need to dig in deeper. Okay. And look for what project this recently funded, when that is expiring. Okay. And major funding agency in US are Department of Energy, EPA, and Department of Agriculture. These are. They also announce what project got funded. So the moment you see that this announcement come and you see where it is funded, this is the time to look for that faculty. Okay, so that will optimize your effort, reduce your frustration, because many a time, even I used to do that, professors will not reply. Okay, and the reason is, if you don't have funding, what to reply? Okay, so make your strategy, look for who are funded, recently funded, go deeper, do some Google, look their website, read what project going on, typically they have duration, and look for anyone. There are Indian association in each university. Okay, almost all university you will find ISA, Indian Student Association. They may have different names, but it's a good idea to connect with them. And they will know more local. Let's say you found a postdoc position, but you need to know many other things, how the living cost, where to live, where to land, and other things. Connect with ISA. They will be very good help for your logistics and many other information you can get. So these are some tips if you use it. Okay. Thank you. Any question?
Sir, first of all, I would like to thank for yesterday's insightful presentations. I'm a PhD scholar working in the area of biomethane enhancement using different agricultural biomasses. So I would ask to what are the thirst areas, particularly thematic areas, apart from the normal that we can approach for postdoc positions in USA, basically. In the field, specifically in the field of bioenergy.
In field of bioenergy means you want to stay in a biogas area.
Yes, sir.
So there are a lot of work going on. Okay, and again we should what I was saying, look for the website where this is going on, where it is funded. Simple Google DOE anaerobic digestion, it will pop up something. So look for those projects, and if I know, I'll definitely tell you right away. In Michigan State University, they have a very big facility and very good projects they have, and all the time they have a very active project. So look for those universities and try to connect with them. So that should be the strategy you want to do. And what you want to do in another university, UIUC, University of Illinois, Urbana-Champaign. They also work a lot in anaerobic digestion. Few more are there. So look for the niche university and then start doing that. Right away, you don't have to ask, I'm looking for postdoc. Do some homework, connect with them, and then you say, this is my interest and all. So you build the relation, and that be more fruitful than sending your resume and say that I'm looking for postdoc, and you may not get any.
Is there any research opportunities for already registered PhD scholars who want to do some portion of their work in your lab or university?
Yeah, so definitely that's a very good idea to do that, and I have been doing with University of Padova, Italy. For last 7-8 years, their PhD students come to my lab, master students come, I go there, this kind of collaboration happen. I work with IIT Roorkee. We are in JNTU and all. So these are the good way to do that. So the question comes how you fund that. Okay, so let's say one semester you want to spend in my lab. So what we do, there are a lot of Government of India, Ministry of Education programs through DST and other. They fund visiting scholars. So they may fund your travel. We may support your lab expenses and experiments and other thing and something like that. And definitely all of you should be looking for that at least a semester out. And I have seen opportunities a lot here and less competitive because they don't get a lot of applications. So I think you should try that and look for Indo-US Science and Technology Forum, IUSTF, Fulbright. How many of you know Fulbright? Yeah, so don't be shy of applying to Fulbright, okay? And go. It has a good success rate. And there are a few more, so do some search and DST, DBT, they have all these programs for sending. It's not, all these institutions want to train you, okay? So take it like that. So if you have a right proposal and that's where comes your contact. If you are connecting me before application, I can guide you what to propose, how to write and other things. I can have another look and maybe I'm not the right in your area. I can connect you to chemistry department or someone. So that's where you should do some homework, and it's a really good idea during PhD spending a semester in US. Why only US, Canada, or many other, UK also. Yeah, so that's one. I'll be talking here also. If can we have MOU or something like that? So that's so funding entire program becomes costly for anyone. Okay, but supporting part by part, someone pays your travel, maybe university pays you something else. So that might be a way to go. Okay. PhD roadmap is very simple, straightforward. If you are looking for PhD in US, do your TOEFL first, TOEFL or IELTS, whatever you like. Okay. If you are emailing anywhere and you don't have TOEFL, it's a breakpoint. Okay, they cannot evaluate your application, so that's done. Okay, so write your TOEFL as early as possible. GRE, I will not worry too much after COVID because many universities that don't require GRE. So when you are looking for, look for university which is not requiring GRE, and then parallelly start applying, and then when you are done with GRE, you can apply other places. The third idea is what you want to do, and it's very similar to postdoc. Which professor, which university you are looking for, and then if they are funded, recently project. So any project funded, like here, we need students to work on that. We don't work directly on that. We need students or postdoc to do that. So definitely we are looking at that time, and it's tough to find right students at right time. Okay. So again, timing is right. Do your homework, find out when they are funded, email at the right time. So that's the way to go. Okay. Yeah, I'll tell you a few more things if I remember. Okay, but this is the way to go. Okay. Yeah.
Thank you, sir. Now it's time for a short tea break. Please be back in 10 minutes so that we can begin with the next lecture. I request everyone to kindly settle down as we begin with the lecture of Professor Sandeep Kumar. Sir, I request you to continue with the lecture. Yeah.
Informal Okay, so we have quite busy day today, and you can see the list here. And I started yesterday preliminary data or connecting chapters, and the idea today is covering all the chapters, and they are very related. Okay, so it's very difficult to distinguish this versus this, so it's kind of mixed, and we'll stop at the time and we'll be more interactive again. The slides are there, it will be given to you at the end, and be more interactive so we learn more. Okay, so today when we left we were talking about organic waste properties, how they are different and how to. Okay, so let us start where we left, different organic waste types of renewable carbon and fuel production. Solid waste, all of you know we generate solid waste, am I right? Every day at home and office, everywhere we do that, and many of those waste are organic or metals. If cannot separate here, let's see if we can separate at certain facility, then we have organic waste such as a different line for fuel, and metals which can go for recycling. So there are many concepts. You can say that organic waste, bio waste, recycling, go heat. Heat is the easiest thing to make. If you have organic waste, you just burn it and you will get heat, make a steam, that's the easiest one, but it's a low efficiency, low value thing. It does not have, if you make fuel, that's a high value, you make carbon, that's a higher value. Okay, so bio waste recycling, we can get heat, and non-organic waste can go for recycling. Non-recyclable waste goes for landfill, and you know landfill issues, am I right? So you don't want to put lot of organics there. Metals, glass, papers, plastic can be sorted out and recycled. So the major challenge is we get everything mixed, how to separate that. Once we know that, the second challenge comes, we have a variable feedstock which has a different property. Let's say organic. Organic waste does not mean it may have paper, it may have fruits, it may have vegetables and many other things. So that's a mixed feedstock. Supermarket organic farm, there's all these things. So how can we do this separation? And then so the property matters, and that's where I left yesterday. There are many different pathways. We'll come that you can use biological platform, biochemical platform, you can use thermal platform. So both are commercial processes. Biochemical, what are the things commercially we produce biochemical way? Can you tell? Using biochemical platform like fermentation and all, what we produce commercially? Biogas, all right? Even penicillin, pharmaceutical things, all right? So we know how it operates. Only thing for feedstock like this, how to tune that. Thermochemically, how many processes you know thermochemically, what we do, what we produce thermochemically? Thermochemical means temperature, pressure, catalyst. Most of the product you see around thermochemically, because that's how we learned. Microbe we learned over the time, last 60, 70, 100 years, but thermochemically we know from long time. The best example is refineries. All right, oil refinery is thermochemical. They use temperature for distillation, they use catalyst, and they use certain times pressure for hydrogenation and all. So what we are looking at, can we take biochemical route or can we take thermochemical route to make products, or can be hybrid, part of it is bio, part of it is thermal. So these are the pathways, and you can see that one is given bio, this one is renewable methanol you can make using electrolysis and catalytic methods. This again we, so I take how you, parts of organic waste valorization. Valorization means making product, upgrading out of it, how you add value to that. It's a lot of waste. Is there any question on environmental benefit? If we take organic waste and I say let's valorize, that means it has environmental benefits. Am I right? There is no question, doubt about that. It's going to help. Then it has economic opportunities. What economic opportunity it has? Can you help me? You are making product out of it, so definitely you are getting some revenue out of it. It's a business model. What other things you get? Yeah. Yeah, that's perfect. Yeah. Job creation. For job, we go to Delhi, Mumbai, and all. Right? Now you can have job creation next to your city or town, where renewable energy, this kind of setup is called distributed system. You can create job. Rural economy can get benefited. All right. So economic opportunity creates value to waste stream, supports green jobs and industries. And this one we talked how it's a circular thing. Petroleum fuel and biofuel, how they are different. I don't want to repeat those. Yeah, this one we are talking. Biomass conversion can have a biochemical or thermochemical. When we talk biochemical, what's the benefit of biochemicals? What advantage biochemical has and what challenges biochemical has? Come on, from biochemical side, who is already working. How you tell refineries that let's do biochemical way, it's better. So what better you say? So it's a low temperature. All right, that's what the best, one of the most important advantages of biochemical. What other benefits? Easier to operate once you know that. You don't need a whole lot of complex systems. You have a, what's challenges? Maintaining optimal conditions. All right. How far? Yeah. Yeah, inhibitor and also difficult to maintain culture. It may crash and everything gone bad. All right. So that's a complexity. How fast it is? 24-hour fermentation is common, am I right? 12 hour, 24, 36 hour is common. So to get a product from beginning to a start, you need to wait a day, am I right? So that's a challenge. Then the thermochemical person will come, or professional will come industry. We make products in half an hour, 30 minutes, 20 minutes, 1 hour, 4 hours, not more than that. Have you seen any product thermochemically coming in a day, 72 hours? No. So that's their benefit. The challenge is high energy requirement. So you pay for energy, temperature, pressure. So equipment or material cost is bigger. All right, you need high temperature materials. So that's the major difference which one you choose. Okay, but you cannot plan everything for thermochemical. You cannot plan all the products is good for biochemical. So it depends on what feedstock, what conditions you want to run, and where you want to operate. knowledge base is in both sector. Fermentation has been century old, how to do fermentation. Okay. Thermochemical, again 100-year-old or more, am I right? There are big refineries, they know that. So if you are a refinery guy, let's say Reliance or HPCL or someone, and there you want sell your biochemical process to them, that is outside their comfort zone. All right. So they may have a wing for R&D and all, but when it comes to commercialization, they may acquire some firm instead of being your own. Same thing for biochemically. They will not try to go to other side because that's the comfort zone. So that's where it challenges comes. So chemically, the combustion is the easiest thing to do. You burn it, get heat, make a steam and do that, but that's not efficient way of doing that. You don't make product, you make heat. Heat has low value. If you look at thermodynamically, heat is high entropy. High entropy is a low value. Okay. Pyrolysis you can do, then different products from pyrolysis I will be talking down the line. You can do gasification, you can do, you can gasify again different products, I will talk down the line. So these three you can do. Biochemically we can do anaerobic digestion, biogas production or alcohols, ethanol, methanol we can do. Even dark fermentation for hydrogen and other things we can do. How bioethanol, I will come down later. Biodiesel. How biodiesel is made? Anyone? So diesel is longer chain than petrol. If you look at the chain length of carbon, diesel is 14, 15, 16, 12. Petrol is C7, C8, 8, so shorter chain. So if you are looking at diesel, vegetable oil, waste cooking oil, grease, they are a good source of, because they have a long chain fatty acids. So you take long chain fatty acids, use with some caustic, sodium hydroxide or KOH and methanol, and this process is called trans-esterification, and that's how we make biodiesel. So it's a very similar to, it's not high temperature process, 60 degree or something like that, you can do that. Okay. It's very similar to alcohol production, beer fermentation. So it's not big deal. You have a sugar, you can ferment, get beer, alcohol, these things. Biodiesel you can get it from vegetable. Challenge is, do we want to put vegetable oil for making biodiesel? No, we don't want to pay more for safflower or canola or mustard oil, am I right? That will go there. Waste cooking oil can be. Now there are many seeds which we don't use for, those seeds can go. Now biodiesel and ethanol is a blend fuel. You understand, blend fuel means you blend it. It's 100% not there, means you cannot fill 100% ethanol, no gasoline and run in your own car. No. Then you have to change engine and everything. So that's not dropping fuel. Same thing for diesel. Biodiesel is not drop-in fuel. It is a blend fuel. You can blend 20%, 10% in jet fuel and other things. So the concept for future is, first don't use vegetable oil, use non-vegetable oil which is not. For ethanol, don't use a starch, use lignocellulosic, what I was talking yesterday. Those are advanced generation. And now more traction in going on more than ethanol, get direct petrol from cellulosic, or take ethanol and upgrade to petrol level. Okay. Because ethanol is not dropping and everyone looking for 100%. We don't want to change, car companies will say will not change the engine, it takes a lot of things. Okay. Same thing for biodiesel, the focus is gone. Biodiesel we learned how to make, it's a blend fuel, but if you want to be more, look for drop-in fuel. So that is called renewable diesel. Okay. And I will talk about that. So that is drop-in, and you can make it, but that is not trans-esterification process, that is hydrogenation process, and again I will be talking. So that's the difference. And here you see micro algae sitting here. Micro algae can be used for So I have a full talk on microalgae, we'll go there, but microalgae contains oil, so that oil you can take it and make transesterification, you can do biodiesel. Again I say biodiesel and ethanol are first generation mostly. We are looking for drop-in fuel where we don't have to change our infrastructure. Refineries, they know how to take and run through a refineries. Pyrolysis, when we do biomass pyrolysis, you get three products: gas, oil and char. Okay. Gasification, we get syngas to hydrogen. So again I have separate talk on gasification. These are just hydrothermal liquefaction or hydrothermal process. That's where my research mostly I have worked in fact my PhD is on that. So what is hydrothermal? What is the major challenge of food waste or algae or this kind of thing? You have lot of water, and now we say do pyrolysis. Doing pyrolysis of water means you make a steam and then little bit of fuel. So the solution is remove water and then do pyrolysis. That becomes energy intensive. So can we do that chemistry used in presence of water? We say don't remove water and do thermal process. So it's called hydrothermal, where water becomes green solvent. It's kind of methanol, act like ethanol, and it can be green solvent. So again I will go more detail, but you can use hydrothermal process and you can make char, acetone, water soluble biocrude. So biocrude is more like a crude. MSW and all, industrial organic waste, energy recovery, these are more common. So waste to fuel technology, anaerobic gas, fermentation, pyrolysis, biochar, bio-oil, gasification is syngas, synthetic gas. Again we will talk about that. Biodiesel is transesterification process, and I say that gasification is the first generation, how to get drop-in fuel. Challenges. Getting technology is one component of turning into a business. You have lot of other things, cost, finance, policy, who will fund it initially, who believes in it, go for loan, will they buy it, your idea or not. Community participation, lack of awareness, lack of technical expertise, logistics, all these issues comes up when we design as a product. There are tons of numerous environmental benefits, economic and social benefits. These are more, I'll skip through case studies and then I'm coming to main topic. But some examples, National Bioenergy Program, India has it, all right. Then Waste to Energy Program, they have it. They provide financial assistance, biogas program, National Green Hydrogen Mission. These are the funding major Indian waste to energy products. NTPC is a lot of work doing. I have seen HPSC, IOCL doing, HPLC doing, HPCL doing. There are other plants, biomethanation plant, IOCL is doing methanol project, CO2 can be converted to methanol. Then private sector, I have seen Reliance very actively doing for last 2 decades. Definitely they have a lot of focus on LG to fuel, drop-in fuel. Tata Steel is doing waste valorization. Adani Group started bio-CNG. International collaboration. There are many Indo-EU projects, Indo-UK project, Indo-US clean energy project, Indo-Japan projects going on. So this collaboration brings you new ideas and it's kind of takes you out of comfort zone. We are working something, you are working something, where is the crossover? And that helps solving a lot of things. So challenges, future map, it's okay. Future trends is okay. Now I come to here. So if we are given a land and asked to grow corn, and we will say this corn is bioenergy crop. We are growing this corn or whatever grass or something just for bioenergy. How much ethanol can be made, or how much biofuel can be made? What would be the yield? That's the first question comes, all right? That comes to efficiency. So let's say corn, if we're talking corn has 60 to 70% or 75% of a starch. Only a starch will give you the kernel or a protein part of it, corn oil will not give you this, all right? So you have to have a biorefinery approach. What other products can we make? Okay. So DDGS and distillery grain and other things you can do. Protein content. So what is the proteins? Wheat, barley, sorghum, oat, rice, these are all first generation. And it depends how much ethanol yield you see that. You should be able to calculate yourself by just writing that formula, glucose to ethanol fermentation, how much you make. Glucose to ethanol fermentation, you know, C6H12O6, you get C2H5OH plus CO2. So this many kg will give me this much ethanol. Now you put efficiency factor, then this much glucose is needed. Once you know how much glucose is needed, you calculate back how much starch was needed. Once you know starch was needed, you know how much starch in corn, so you know how much corn was needed. And now you know productivity of corn per acre, how much corn you can produce. So you know how big land is needed to set up a biorefinery. So in fact, this you can build yourself, and that's how you design a plant. And once you know I need 100-acre land, now you go to techno-economic. What would be the transportation cost for such a big hauling area? So feedstock cost, another thing comes. So let's go through one example. A starch can be represented C6H10O5N, and a starch is polymer of glucose and hydroglucose. So you see C6H10O5, it will undergo through hydrolysis process. That means you will add water, H2O. So that H2O, 2H2 will come here, so this will become 12 and this O5 will become 6, and then you will start opening chain. So anhydrous glucose, add water and it become a starch to this. So where the degree of polymerization, because N can be 1000 or 10,000 even, it's a long chain. What would be theoretical maximum yield of glucose and ethanol from 1000 kg of a starch? If 100% is assumed, that is ideal, you don't get 100%, but just to simplify, during start to glucose hydrolysis, glucose to ethanol via fermentation process. So there are two steps in making ethanol. A starch needs to change it to glucose and glucose to be fermented to this. We should be able to estimate, calculate and tell the policy maker that you need this much land, this much corn productivity in this area. This is corn, it can be sugarcane also. All right, it can be any other starch source or sugar source. So a starch molecular weight what would be? C6H10O5. C6H10O5, let's forget N right now, we don't know N. Glucose 180, we just remember. Ethanol 46, we remember, but you can calculate. Okay. Now what is hydrolysis reaction? You add water, so you need N number of waters, it will become N number of glucose. So now this is, because it is missing water 18, so you 2 only, and then it makes 180. So if you have a starch, you will get glucose 1.1 times. So if you have a 1000 kg of a starch, you will get 1100 of glucose. From material balance, you know that in plus out should be same, in or out should be same. But here it is not same, you are getting more because you are adding water. So when you plus water, it is same. Okay, so water is increasing the value. Then we come to fermentation. So you got C6H12O6. Fermentation gives you 2 moles of methanol, ethanol per mole of glucose. So now you can go back, calculate, and this is roughly half, 51%, if you see that. So 51% you will get. So 1100 kg of glucose, I am rounding, 1100 kg converts to 567 kg of ethanol. Okay? Assumption is 100% efficiency. It may be 90% because many things, fermentation conditions and mass, viscosity and other thing matters. All right. So now we are able to calculate 1000 kg of starch will give you that much ethanol. Let's go back. Corn has 22% starch. So now you can go back and say how much corn you need. All right, of that. Once you know corn, even farmers will tell per acre how much corn you can grow. All right. So now you know how much land you need, how many rotation you will do, how big area, then what size of corn and ethanol refinery you can put. So once you give all these numbers, then there is a techno-economic guy who will be doing all, plugging these numbers, build a flow sheet, and you see what materials coming in, how far. So they will say it's economical or not economical. So that's how you go. So yes, very basic you will see. It can be more complex, but this is how it's calculated. So US corn, they are sold in bushel. Yes, bushel is, we are more common there is pounds, not kg. So 1 bushel is 56 pound or something with 15% moisture. Any time if you are dealing with organic material, waste or corn and whatever, always keep an eye on moisture, because you are paying for corn, not for moisture 15%. So you are looking for moisture free, how much material we are getting, but it's not moisture free, water will come with that. So price should be adjusted accordingly. If you have 30% moisture, then price should change. So per bushel, which is 56 pound with 15% moisture yield, same math we have done. Okay, you can come out with this, which is handy for farmers. Now they don't have to do those math. So per bushel you will get about 2.8 gallons are common, not liters there. So 2.8 gallons. Then feed you will get proteins, gluten meal, corn oil you will get, corn has oil. So you can have a ethanol biorefinery and you can get all these things. My point is how to estimate. If you are helping an industry as a process engineer or biology side or whatever, how much you can produce, they are looking at you. So let's come to here, lignocellulosic biomass, which I started, and this is what I am saying, that this is the future. Starch is not the future. It will go, but you cannot build multiple plants on starch. Vegetable oil, sugarcane juice, no. So all these materials, what you see, this is woody. This is wood, am I right? This is more fibrous, sugarcane. This is more grassy, all right? Here we will find more silica in organic material. In wood you won't find much silica because the way it grows. Yesterday I started that discussion, I am coming back because it's very important to understand what it is. So if you take a log or chip or something and you want to put a microscope and simplify how it looks, cellulose is a straight chain of anhydroglucose, C6H10O5N. And how it's different from a starch? You remember I gave you 2 lines, and one is a starch, one is this, one is alpha, another is beta, 1,4-glycosidic bond. Beta makes you fiber, very strong, alpha makes you easy to digest, and that goes in our intake also. We say carb versus fiber, it's a truth comes from here, knowledge comes from here. Okay, so this is your brick. Hemicellulose is also glucose, sugar, but that is not single sugar. If you have cellulose, you can hydrolyze it, you will get only glucose or oligomer or dimer or something like, but they are only on glucose. If you hydrolyze hemicellulose, they are branch, okay, and they are mixture of sugar. How many sugars you know? Anyone? Besides glucose, what else you know in sugar? Lactose, mannose, sucrose, fructose, xylose, arabinose. These are all sugar. And when you hydrolyze this, you will get mixture of this. And plus organic acids, acetic acids, they are branch here. So now you see the difference. If you have a starch, you can hydrolyze, you get glucose, nice clean fermentation, ethanol, no worry. If you hydrolyze this one, you are going to get mixture of sugar. Now we design Baker yeast, which likes glucose fermentation and takes it. Will Baker yeast will take this mixture of sugar? It won't take, it will be very slow, inefficient, all right. So now the challenge comes. We are trying to digest something like a woody or grassy material using biological pathway. Now we have to look at right enzyme mixture, cocktail of enzyme, which will do effective for multiple sugars. So a starch or potato easy to make ethanol. This one comes challenge. Not only that, the outer layer is lignin, and lignin is aromatic. Lignin is called young coal, brown coal. Basically, coal when is formed, is basically lignin is the starting point. So can you ferment coal? Can you biodegrade coal? No, you leave it outside, it will remain coal, all right. And that's the very close to that, not exactly that, but a young coal. So now you see the challenge. You have to do very clean separation to get cellulose, like paper industry does. They are worried about these fibers. They don't do hydrolysis, they want to protect it as it is, they don't want to cut it. But for ethanol, we want to cut it also, release. Enzyme goes and do that. And we want to stay away from lignin because that is going to reduce your efficiency. It won't be biodegradable, means it won't be digestible, plus it will inhibit, it's aromatic. So ask a company and ask for business, they will say, I'll take sugarcane juice for ethanol making. Bagasse, it will be costly. Commercially it is costly. That's where we are looking at you. What kind of enzyme, what kind of process condition, how you will expose this fiber such that enzymes work efficiently. Even if you have a right enzyme for this, you have to boundary, all right. You have to do some pulping or something so that lignin goes out, then only enzyme will work. So this is the challenge. And depending on feedstock, whether it's wood or whether it's a grass, this value changes. These two together about 65 to 70% are carbohydrates, carbs. This is aromatic lignin. These are inorganics, extractive, those kind of things. And we are looking biochemically to do this fermentation biological. So that's the challenge, finding a right enzyme, right microorganism, such then we go to fermentation route. So look other way, if we go thermochemically, what will happen? We will not recognize it is hemicellulose or lignin, we will break down everything as a carbon, hydrogen, oxygen, nitrogen. Use heat and change into gas and something like that. Pyrolysis. The yield will matter, but you can do those things, all right. It's not very sensitive to what you have. So should we go thermochemical route? Should we go biochemical route? It depends what feedstock you want, what efficiency you want. That's where we decide. So let me know more on this. I already talked. So hemicellulose, if you want to represent, you call it GIAN. Okay, GIAN, and carbs are called glucan also. Glucan. So cellulose, some people call it glucan because glucan hydrolyzed to glucose, so we call it glucan. GIAN hydrolyzed to xylose, so we call it. It's a mixture of sugar, but xylose is more, so we call it GIAN. Okay, this fiber are microfibrils and their dimension are 10 to 30 nanometer. This is very simplified arrangement, brick mortar arrangement, but it's more complex than that. It interferes with, it's called lignin carbohydrate bonds. They are bound together. It's not such that you chip it and it will go out. So 2 units of, if you take, is called cellobiose. So some people call cellulose is a multiple unit of cellobiose also. That's fine. Tell me purest form of glucose. Cellulose. If you go tree and you get cellulose, you have to do something, pulping and release it. The purest form of cellulose is cotton, white cotton, right? That's pure cellulose. That's pure cellulose, and how strong it is, you know. But there you can design enzyme to break it down because it's not contaminated with other things. Its degree of polymerization can go up to 7,000 to 14,000. Paper industry keeps an eye on that. The longer, the better fiber or shorter fiber, what they want to make it. Okay. These units are cross-linked fiber, but intra-bond and inter-bonds are the hydrogen bonds are there. They are linked together. Why I am bringing those things? If you are looking at biochemically, what are the bond needs to be cut to release glucose? Hemicellulose, I already talked all these things. It's a mixture of sugar, pentose and hexose. Pentose means 5 carbon sugar, hexose is 6 carbon sugar, and then you have a branching, you will see COH sitting, that means organic acid coming out. So when you cut it off, digest using enzyme, you will get mixture of things. The good point is it's a softer, it's amorphous. So at low temperature gets loss removed. 180, 200 degree hot water wash will take it out. But nothing will happen to cellulose at that condition. So you can fractionate. Now this has commercial use. Furan chemicals made from that. Okay. Furfural is a chemical made from hemicellulose. So that's how it does. You separate cellulose, lignin, and hydrolyze this, and you can get furan based compounds, and you change it to furfural. So that's a finished product, an industrial product. So hemicellulose is not long like cellulose. This is a small chain, branch chain, mixture of sugar. There are many side groups. Lignin. So a straight chain, nice cellulose fiber. Hemicellulose we could understand. Now you understand here what you see. This is lignin. This is lignin, this is the representation. What you see. When you saw cellulose, there was repeating units of glucose. Hemicellulose again repeating of different sugars. What you see repeating here. It's built on something, am I right? A repetitive unit, it's a polymer. Closely, we'll find these true monomers. Lignin are built on that, and these are aromatic. Okay, that's inhibitory for many things. Lignin properties, its molecular weight or degree of polymerization is not like cellulose. It's different bonds you will see, CC bond, COC bond. If you want to represent as a formula like cellulose or a starch, we represent C6H10O5 whole N. If you want to write lignin somewhere, this is the way to write C9H10O2 OCH3 is the repeating unit. Now you can do material balance because you need formula for those calculations. You can represent that, and it varies. So if you are looking thermochemically, how much? So all these things, why we are looking? They are renewable carbon. All right. I'm going more deeper, cellulose, semicellulose, but as a bigger picture, they are carbon, renewable carbon source. So you are looking at what percentage carbon you have. In lignin, you will see 60% carbon, 59 to 60% carbon. Tell me what percent of carbon in glucose or cellulose? If you are given glucose, can you tell me what is the percentage of carbon in glucose? C6H12O6, it's 180, all right. C6 72, 72 versus 180 is 40% carbon. Okay, so that is your renewable carbon for any use. 40%. Cellulose little higher because oxygen is O5 not O6, so it is 44% in that range. Lignin, if you are looking at a just carbon, keep an eye, it's 60%. So that's why you will see that ethanol refineries, bagasse or leftover material, they burn for heat. All right, leftover after ethanol, they burn for heat, run for electricity. If you are burning sugar for heat, not much because it's less carbon, but here lignin will give more energy because it has more carbon. So you, one of the easiest thing you do, burn in the refinery, get electricity, support the heat. That's how that model. But that model can be improved if you can take this leftover material, make furfural or ethanol or another thing, then you have more value to it. All right. Liquid fuel have a more value than solid fuel. And yesterday I talked why, because handle easy, content, per unit volume you have more energy, heating value and other things. Byproducts market you will not realize, but there are many products which we are already using. They are commercial. Glutamic acid, glucaric acid, glycerol, these are all furan based chemicals. Furfural should be here, HMF should be here. So there are many chemicals is being made. Okay, it's not something, it's not used. We are looking for what more commodity things we can make. This is from Second World War. This bus is run by gasifier, and I will show a few more. Germany, how much oil they have? Not much, right? They import. But how much wood they have? A lot. During war time, fuel is the main thing you want. War will stop if you don't have fuel. You cannot fly, you cannot move. So they came out with fuel cut-off thing. So they came out with why not use wood for gasifier and run our transportation system. So that's where it started. Economic issues of bioenergy conversion. What is the cost of biomass? There are two kinds of feedstock. One, you are growing or buying from farmers, making fuel out of it or products. One, you are getting free and you are hauling to some location and making product out of it. The product which you are getting free, you are paying money for transportation, for water and other things. City cannot dispose, so you are coming as a contractor, I will take it and make fuel out of it. The other place you are buying grass or wood to make fuel out of it, and the cost differs. So that's where economic comes, what feedstock you have. Okay. So project of biomass, projected cost versus heating value. This business energy is heating value. How much heating value you have, and based on that you will pay price for wood. Cost of energy derived, how much cost of biomass versus how much energy conversion you do, efficiency. So viability of any project for following several items: cost of electricity, how much electricity it needs this process, how much return you will get. Go to a business, anyone, what is IRR, investment on return on investment. If it is not attractive, they will not put money on that. Even you will not do that. So that's one thing. Net present value, payback period, how soon I will get money back. Okay, life cycle cost. So those are the thing guides how the business or how to set it up. Okay, now let's continue with the property and characterization. We learnt what it contains. I give you wood chip and now you will say it has fibers, cellulose, hemicellulose and lignin. Now I will ask you how much cellulose it has, because that's important. Saying that it has cellulose is just give you some idea, it does not solve anything. All right, it has lignin, it gives you some idea, but how much lignin you want to know, how much hemicellulose you want to know. If you are looking at a renewable carbon, how much carbon it is, how do you analyze, how will you put number to these values? That comes to lab analysis, how we do that, how we characterize it. Okay. So if you look at, there is no single number. You bring corn, you bring sorghum, bagasse, hardwood, softwood, switchgrass, they are single numbers. So you can design a plant for bagasse, and then someone comes, why don't you take woods in it? Then you have to tune the plant to match the uniform feedstock and do this. So things changes. Okay, so now there are two kinds of analysis. If you are biochemical, you are looking at how much cellulose such that you can calculate how much ethanol you will get. If you are a thermochemical, you are looking at how much carbon, how much oil it can produce. So let's go one by one. So for biochemical, cellulose, hemicellulose components are important, or lignin how much, because those will give you alcohol. So how do we analyze cellulose? Anyone? Have you done biomass analysis in your lab? Pardon? When? Yeah. So the very basic method is where it has started. Lab analysis method does not lead to a commercial process, because that is designed just for labs. So you don't worry about cost and all. You can be very aggressive, you do that. And someone comes, oh, I take lab process and expand per industry, it won't work. Okay. So what you do, a strong sulfuric acid, 72%, you apply to that. Okay. You do second stage 100 autoclave basically at 100 degree. It releases cellulose to glucose, and then you put in HPLC, high pressure liquid chromatography, and peak will tell you under the area how much glucose you have. Now once you get glucose, you go back how many cellulose was there based on that ratio. Okay, it's all mass balance. So residue measured by gravimetric, but cellulose, why use sulfuric acid to hydrolyze cellulose? Okay, so it's a very long chain. When you start hydrolysis, some may turn to glucose, some may still soluble but oligomer, dimer, trimer and other things. So they are oligomer up to 8 to 10 units. Second stage hydrolysis makes sure that you reach to this. So that's why two step of sulfuric acid analysis application and autoclaving will give you glucose, run through this HPLC area under the curve, and all sugar mixtures you can calculate back, and you will say this much cellulose we have. Okay. The leftover residue is mostly lignin. And once you measure leftover things, is lignin, you can burn it, put in a oven and do the gravimetry. So mass lost of that solid, I am simplifying, there is a complete method how to do that. So giving a bigger picture how it is analyzed. So thermogravimetry, you burn it, the weight loss is lignin, leftover material is ash. So you started cellulose and hemicellulose gives you peak because of sulfuric acid hydrolysis, HPLC gives you amount of sugars. So how much cellulose, hemicellulose you calculated using this, and then leftover residue was mostly lignin, so you burn it and you get how much lignin was there and how much ash. This is how we analyze lignocellulosic material. Now once you know how much cellulose, then you know how much ethanol can be made, how much enzyme you need. So this is a bigger picture. If you want to do in lab, go to these links. Okay, this is called NREL protocols, National Renewable Energy Laboratory. They came out with a method for biomass composition analysis. They have a step by step methods what you need, and just follow that and you will get it. Now come to thermochemical. If you are designing pyrolysis, another thing, what important? Temperature. You are subjecting to temperature. So what is important? Weight loss, how it will happen. All right, how much carbon will remain or gas phase, how much remain in solid, and those kind of things. Then you can do. So for that we do proximate and ultimate analysis. So proximate analysis, ultimate analysis knowledge base comes from coal industry. If you are talking to coal industry or thermal power plant, they are interested in knowing proximate analysis of coal. That way they will know how much fixed coal, how much ash, how much moisture, and how much fixed carbon has. So moisture plus tiles plus fixed is 100%. This is called thermogravimetry, TGA. Many labs will have TGA. So TGA, what it does, you load pan, the instrument heats at a given heating rate. You can decide 10 degree per minute or 20 degree per minute. You look at the protocol ASTM method how to do, and then what it does, time says weight loss, and another side temperature also you can plot. Weight loss, initial weight loss around 100 to 150 degree, mostly because of moisture, am I right? You will see drop in weight, mostly because of carbohydrates, volatiles and other thing will go out. Then it's a very complex mixture. So weight loss continues. Then you are left with fixed carbon, which is not going to gasify at that temperature. So at that time you supply air. This is done without air. Now once you get fixed carbon, you run air. So this fixed carbon will burn the weight loss, and you can get how much fixed carbon was there, and then leftover material is ash. You don't have to remember what you want to remember. This is what proximate analysis is. How to do? You need TGA and you need to follow ASTM method, which is published method. Just download, go step by step. Okay. So now look at this. Most of the lignocellulosic or organic waste, they will look like this. Volatiles more, fixed carbon less, ash and some moisture. Put coal next to it because the knowledge base comes from coal. Coal will have more fixed carbon, less volatiles. So volatile matter, now you can see that fixed carbon, all these things. Now let's come to ultimate analysis. So what is ultimate analysis? If we are doing, again we need to do thermochemical process, gasification, pyrolysis, we need to know how much carbon it has. That's value we are paying for biomass or feedstock. So ultimate analysis is elemental analysis. The name suggests ultimate means you broke down everything, and we are talking at the carbon, hydrogen, nitrogen, oxygen, sulfur level. Okay. So again, these are STM methods you don't remember. I am trying to make you understand how it is done and why it's important. Carbon, hydrogen, nitrogen, sulfur and chlorine and ash, these are measured. Again, it comes from coal industry knowledge base applied to biomass. So all these together, moisture, ash plus all these elements, that's what assume biomass has. These are the major elements, makes 100%. That's the assumption. Now there is an instrument called elemental analyzer. Okay. Again, major companies supplies it, elemental analyzer, Shimazu, Agilent, there are many versions of it. So you can use it, they apply temperature, burn biomass, and then they have detector. So if you combust biomass at high temperature, you will get CO2, am I right? The detector will sense CO2 and tell you back how much carbon was there, so CH2. Same way nitrous oxide, so they will tell you CHNOS values, percentage. You put it that, you will say ultimate analysis. Okay. If you put it like this is biomass, carbon 40%. Someday if you someone in lab, if you are doing analysis and you getting 80% carbon, tell that is wrong. If say raw biomass and nothing done and you are getting 80-70%, it is wrong. Okay, so we should do analysis as one thing. If I bring something to your lab and say give me analysis, first thing we will ask what do you expect, how much you expect. When I was at BARC, we used to do a lot of uranium work. Okay. So we have some samples, we will go to lab, analyze what percentage of uranium compound it has. The guy will ask, I was young at that time, new, so they will ask how much you expect. Then I am taken back, I am bringing for analysis and you are asking me how much I expect. Then I realize over the time that you need to have a calibration curve, you need to understand what is the concentration, they can only analyze. So you need to know the range and that will give you, so you have, this is the range you are working on. Now this can be here, 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 it cannot be here, right, biomass. If you put coal next to it, what will you see? Coal will be here, this much carbon. 80-90% is coal. So if you have a coal and doing analysis and you are getting 30% carbon, then something going wrong. That's why you need to know what's the estimate. Okay, so now let's go to thermal power plant. What they do? They burn coal to get steam and electricity. And we are a smart guy, say that mix some biomass and make green, less CO2, go green, make it, they will say hold on. Okay. You can burn biomass, but if you blend it together, you have a different carbon percentage. All right. That is going to change boiler characteristic, that is going to change the flame length and other things. So they will say hold on, we need to design or something like that, change something like that. The other thing will happen, how do you feed coal to boiler? You have a conveyor belt which goes to put that. How do you feed biomass to boiler? Can you transfer sawdust like coal pneumatically? What will happen? It will transfer, then suddenly it will breach. All right. You have to shake it up, then it will flow, then it will. So that characteristic is different. That's why saying blend 30% easy, engineering wise it's not feasible. Okay, you cannot do. So then you can make char or pellets and then you can blend it. So any bio or organic waste or organic matter, you want to know proximate analysis and ultimate analysis. Why you need to know? Because you can write this formula and then you can do material balance. Now here this was corn stover. Corn stover for me is how much fixed carbon and how much volatiles. Corn stover for me how much carbon? 43%, 44%. You won't see. Alright. So this is the carbon value we are paying for making oil or anything crude or from this. Oxygen, lot of oxygen you will see. Nitrogen, not much, but if it's a protein compound, you will see some. Now this is our biomass, and what is our ultimate objective? Making petrol, gasoline or jet fuel. Put crude oil next to it, how that will look like. Then you will appreciate the advantage of making. If you have a crude oil, how this can look like? Tell me a range. How much carbon in crude oil or gasoline? Definitely double than that, am I right? It's hydrocarbon, right? It's close to 80-90% in that range, double than that. So if you have this is double than that, this will go down, am I right? This is simple math. If you have 80% carbon, this will be 10%, 8% and all. So I am simplifying you. Biomass and you want to make it oil, what you need to do? Can you tell me now? This is biomass and I put a oil and I said 80-90% carbon we have to go. So what we need to do? Increase carbon content, reduce this. That's the chemistry we have to do, thermochemically or biochemically, whatever. Very basic level. How it looks, hydrogen to carbon ratio from yesterday. What is the H/C ratio of oil, gasoline, diesel or all those things? Pardon? 0.2? So methane was, how much was methane? CS. You want to make this oil, and I should have put another table for oil, then it was easier, but imagine now carbon need to go 80-90%, hydrogen need to go H/C ratio 2. Okay. So what we have to do? So let me take a step back. If you want to do material balance, you need some formula, chemical formula, how to represent, then you do material balance. So once you have mental analysis or ultimate analysis, you can write this formula. Biomass, once you have done that, you can represent like this: C, H 1.5, O 0.7, N. It's not magic. What you do, one, change in mole, you can write C4H6, something like that, or you make this one, so H 1.5. So basically it's mole, you change in the mole percentage and you can simplify base 1, then this will look like this. What is H/C ratio here? This is biomass or organic waste, whatever. What is H/C ratio here? 1.5. If you want to make oil, what is the H/C ratio? 2:1. So from 1.5 to 2 you want to go. What you need to do? Math, nothing else. I am not talking chemistry. Forget this. You want to make this 2. Either you reduce this or increase this. Am I right? And once you have started removing this, this will improve. All right. So no matter what you do, you don't want to lose this carbon. It's a hydrocarbon business. You don't want to lose carbon in form of CO2. If you are doing thermochemical, you want to lose it, this will become CO2, and CO2 has no value, oxidized, no fuel value. So you want to protect this, and you want to increase this, and you don't want these things. That's simple how you will do. You need hydrogen to add here. That means you have to do some hydrogenation process. This is hydrogen deficient compound. So you have to do hydrogenation, and what else you have to do? You have to remove this. If you add, this will reduce, but you have to remove this oxygen. This is, in math it is 40%, 30%. So you have to do deoxygenation. You have to remove oxygen, you have to add hydrogen. Then only you can go to CH2 bond of drop in fuel. That's very fundamental level. Much more added in that. You need catalyst, temperature, what temperature, hydrogenation and other things. But the thing is, this is hydrogen deficient compound, oxygen rich compound. You have to reduce oxygen, you have to increase hydrogen. That's why you need hydrogen to add. This hydrogen can come from green hydrogen, electrolysis, and you can be innovative on that. But this is what need to be done, and that's why I was looking from very fundamental level. Now if you are designing thermochemical process, pyrolysis, you will understand better. If you are looking gasification, you will understand better now. Okay, what need to be done. Let's say you want to take this coal, not oil. You want coal, green coal. Because sometimes you want coal, sometimes you want oil. Am I right? So what need to be done to get coal from biomass? Char. If you want to increase char, just you are worried about char making, not oil or anything. What you need to do here? Put a table for coal. How coal will look, carbon percentage for coal. What is percentage of carbon you assume in coal? Very high, am I right? 90%. More carbon, better the coal. And ash, sometimes you get, so low quality coal, it will have more ash, high quality coal will have less ash. So that's why you import some coal we have, we do mixing or something like that. So coal quality matters. You want carbon in coal, all right? Not much oxygen you want in coal. So you won't see oxygen. How about hydrogen? 4:1 is gas, 2:1 is oil, all right? Gas, liquid, now solid. What is the H/C ratio for coal? I showed you lignin there, it's a kind of coal. So what is the H/C ratio of coal? Again, these are very generalized things I am talking. So H/C ratio of coal is close to 1. Okay, CH bond you will see. So the lignin, look very closely, you will see CH bond more. So now to make this 1, you need to increase carbon more, all right? That's why we do carbonize. When we carbonize, we try to retain carbon in the solid form, and that turn into coal, H/C ratio. So you don't need hydrogen there. And you want to remove oxygen, and oxygen when you want to remove from here, in both oil or coal case. Have you seen oxygen? If you heat something, do you see pure oxygen will come out? If you have wood and you are heating and purpose is carbonization, that means you want to remove oxygen. So how oxygen will come out? There is no magic that I will scalp and take it. So you will heat it, gas will form. So oxygen will come as a compound, am I right? Not pure oxygen. So it will come like a carbon dioxide or carbon monoxide or methane, depending on what, or water, H2O. If you are making coal and oil, you want to remove oxygen, but your treasure is carbon and hydrogen, that makes fuel. So in the process of removing oxygen, you will end up losing some carbon in form of CO2, and CO2 has low value or no value. But that's the compromise you have to do. The process you will design where CO2 is less, carbon monoxide is more, methane is more, because those gases have value, energy value. CO2 has not. Okay, so that's called decarboxylation or deoxygenation method. So if you are getting water out, that's fantastic, then you are not losing carbon there, but you are losing hydrogen. So this example, if you see that, we are asking how to do representative formula, how to write that formula. This is just example for you. So it's given CH. Sulfur, nitrogen are always less than 1% low, so you can neglect it for, it's not very significant. So you rest is moisture or ash or oxygen. So you can write ash free basis this formula, assuming 100 all CHNO as 100 and O you will get by difference, 100 minus C minus H minus, and then you can do that, and then you can write that formula HON, get it. So you got O based on difference, change into mole, change this to 1, so divide everything by 4.19, you get 1, and this is the formula you get. You took a strong pyrolysis process, and pyrolysis process what you want to make, either char or oil. So let's say we made oil and we did elemental analysis of oil. Okay, carbon percentage will look higher because that's the purpose you made oil. If carbon percentage goes low, that's not done. So now you look at it, formula will change. You will see higher 3, but this is not 2, this because of these numbers. So once you get it, it's not yet there. So you have to hydrogenate, remove this and all. I simplified, but H by C2 you have to go, and then these things should not be there in oil. Okay, so that's why this oil is not ready crude oil, because that formula looks like this. We think we made pyrolysis oil, that's a crude oil. No, that need further upgradation through hydrogenation or deoxygenation process to get this out, get this out, get this ratio right. So when you made pyrolysis oil, you will see a lot of water in it also. It phase separate, and then you have to take it. So you can use this for heating purpose, low value. You can, this is oil, so you can burn it. Okay, but if you are giving to refinery and make diesel and petrol, it's not ready. They will not take it. It won't blend with crude oil. So the idea, if you are working on pyrolysis, you want to make it stable. This is not stable. It will change over time. So the stability will come with removing this, making more balanced formula by hydrogenation or something. So fuel business is, I said you, energy content. And look at here on this table and tell me what you see. Keep up, top to down, keep looking. Uranium is highest because of it's a nuclear fission, that's a very different topic. Okay, up to here it's all combustion topic. You get energy from combustion, and we want to make fuel, but we want to make gasoline, all right, diesel. So we have to come to 44, where gas 15, 16, those things, all right. So again same thing, if you look at differently, we are here, you have to come here, that means you have to remove oxygen. Do thermochemical process or biochemical process, you have to come out like that. Okay, so lower the oxygen content, higher the heating value that you want to remember. Now, I was talking yesterday, many people don't like ethanol. 4 different regions. The one region is heating versus 44. If you mix 44 and 30, definitely average will come down 35, 36. That means that much sacrifice you want to do. If you need 1 liter petrol, now you will need 1.2 liter petrol for driving the same distance. Okay. So if I talk like this, then they will say no ethanol. No, it's not that simple. Now this ethanol is renewable. Okay. 5 to 10% in ethanol helps clean burning. Okay. If you don't have this any oxygen here, it's a soot formation. So typically MEA or something we added in blend fluid, gasoline blend thing we do that, additive we add it for clean burning. Now you don't need that additive, ethanol that because of it brings some oxygen. So it helps clean burning, less soot formation. Okay, so you compromise that, but combustion is better. If you start increasing this percentage, this number average will still coming down. So how much you can blend? That's why I'm saying ethanol is a transition route. Everyone is looking for drop-in fuel. I don't want to reduce. Can you make these things right here, not here? And that's the future. That's a drop-in fuel or fungible fuel we are talking. So you will see many projects, they are taking ethanol and making thermochemically catalytic method, diesel or gasoline, right drop-in. Okay, but if you are doing that, you are adding cost to it. So how efficiently you can do, how good catalyst and all, that's such topic. But that's the thing, and if someone is telling ethanol is not good, this is the way you have to explain. It does good at certain percentage or how it is. It is renewable, which has a much better value environmentally and other things. But that's why it's a blend. We don't go 100%. If you go 100%, how much compromise you will do in mileage? Am I right? And plus this oxygen, and oxygen is reactive compound. So it will swell your gasket and other things. Ethanol loves water. Diesel does not like water. All right. So if you are, so ethanol, you will see another challenge. How we transport petrol or crude oil, pipe. Have you seen ethanol pumped on pipe? Why? Always you will see ethanol coming from tanker. Have you thought why? One thing is volume is not that much that you should be pumping so much. That's one thing. But from here to there, you can pump it. Second thing is likes water. It's beer basically. You can dissolve and you can. So if you are pumping, moisture will play a role. Pipeline over the time, water will seep, so moisture and also that will deteriorate the quality. So that's another challenge of ethanol. That's another challenge of moving towards dropping. Tanker supply will not address country level demand of fuel. Am I right? You need transportation, piping and all. So again, that's why we are moving away from ethanol for a drop-in fuel in future. That's the way. But I'm not no way saying that ethanol is not good. Blend is always fine. Look at hydrogen and natural gas. Natural gas is 54, pure hydrogen. So now you will say, why don't we have hydrogen car? Green hydrogen car. You might have seen fuel cell, hydrogen cars and other things, and then some things are slowed down, some things are picked up. So hydrogen car is mainly someone is looking at this number. So you need less of hydrogen to drive same amount. Okay. Then it's gas you can compress. So high pressure you can do, and it's clean burn. So it becomes water. So there is no pollution. That's why we are looking at hydrogen. The challenge is light gas. It's a light gas. So you have to compress. To fill up hydrogen in this room, it won't much. Unless you compress it, you won't get value. So you need high pressure tanks now for vehicles. It's like a high pressure container you are running. The second challenge is, how do you get hydrogen? Oil you drill and then refine, you get it. How do you get hydrogen? Pardon? You have to split something. Hydrogen is not freely you go mine or drill or something. You won't get it. It's not free compound. It's always a carrier. Fuel cell works on hydrogen. But fuel cell is good efficiency. But how do you supply hydrogen to fuel cell? You need a fuel to make hydrogen. Okay, so it may look fuel cell clean, but you are shifting how you get hydrogen. So hydrogen is very good fuel, but it's a carrier, energy carrier. You don't get free. Natural gas is a fuel because it occurs. Methane is naturally occurring, not hydrogen freely. Okay. Then H by C ratio, which I already talked, all these things. Atomic ratio, why is important, I just now talked. So this is typically we do for biomass, coal or energy business. This is called Van Craveland diagram. If you are publishing something, you have done some analysis in your manuscript, you plot Van Craveland diagram. Look at that angle. How H by C ratio versus O by C ratio looks like. O by C versus H by C. It has a lineage from coal industry, but this is common way to represent your results and to start discussions where we are. So biomass is here, H by C versus O by C ratio. And you can plot it because we did ultimate analysis. From there you can do H by C, and H by C you will see this. Okay. If you are looking for solid fuel, to anthracite best quality coal is here. All carbon, very low oxygen, very low hydrogen. So now you did something and you want to look where we are, then maybe it will look like this. Okay, I need to go this far, what you are making. So Van Craveland diagram, you should be a good way for data representation or data analysis and other things. Heating value, how do you calculate? I forgot to mention how you do heating value. Oh, I gave you a few biomass and I asked you heating value. Tell me what is the heating value. How will you tell that? We know wood had 50. How do we measure that? Have you heard about bomb calorimeter? So it's calorimeter which burns in presence of oxygen and is calculated back heating value. Okay. If you don't have bomb calorimeter, OS, that's the estimation you can do. You don't have to have calorimeter heating value. There are many empirical formula you can Google. One of those is called Dulong's formula, which tells how much carbon, how lower heating value. Yeah. H by C ratio, large mass expressed in linear, how is mass? Bomb calorimeter was thinking. Okay. If you don't have, still you can use CHNS method and Dulong formula, you can do that. Heating value are two types, more on reading material, I don't want to go there, it will take time. So Durand formula, one form looks like this. These are not universal formulas. These formulas are for biomass, wood, grass, different goal. So you will have to look at right empirical formula which fits in your range, and then we have an ultimate analysis. You can put those numbers and you will get higher heating value. So it's another way to look the what you made it, char. What's the heating value of char if you are looking at a solid fuel? If you are looking for land application, that's a different. But if you are looking for solid fuel, you need to look at heating value. Moisture, how you, because all these things has to be traded in market. How much price you want to pay. Some always 200 rupees per kg or ton as received. You take it from here, give me 200 rupees. Now you need to know taking it a 40% moisture or 10% moisture, what price I am paying for that. So that is as received pricing. Air dried pricing. If you do something air dry, how dry you can go? Can you remove entire moisture? So what percentage close you can come? If you air dry some food item or something, you think all moisture gone? No, some moisture will remain, but you can have a good number how much air dry you will have, 2%, 3%, 5%. So that's the pricing called air dried price is 1000 rupees per kg. So you know how much price I am paying for water. Dry basis, all moisture removed in a laboratory analysis you did right away and you say this is the moisture. So dry basis you can pay price, that will be little. Now ash free basis, ash is another thing which is not going to give you fuel. So are you buying grass or are you buying some wood? Ash is different. One is 10%, another is 2%. So you want to base your pricing on ash free basis, because other is inert material you don't want. So this is how it's reported. What are the things in ash? Aluminum, iron, calcium and other things, so all inorganic. Bulk density. You see this? That's how bulk density matters. Denser material or less dense material, one truckload of pelletized or as it is material will be different. So you want to know bulk density because it's being transported. So how we measure, it's easy. So you go through that. True density, apparent density, biomass growth density. I am not going through these things. Thermal conductivity, if you are doing material and other things, then a specific heat, thermal processes. I have given one example. We have assumed formula of biomass, you will see that, and it will ask heat formation, other things. So it's not relevant. Okay, this one is more relevant. How will you do mass balance? Let's say this is the truck, this is the plant, truck comes and solid fuel out, green coal we are making. So this is the black box, right? Here we are doing some pyrolysis or something. So I bring 1 ton here, biomass, maybe you are getting only 200 kg of coal, green coal. What happens to 80%? You have to design the plant, this plant now. Where this 800 kg goes? If you have 1000 kg and you get only 300 kg, what happens to another 700 kg? Where they go? It's like our money. If I earn this much, 1000 rupees today and tomorrow I have only 100 rupees, where 900 gone? You need to know. That's mass balance. Based on that, you will design pipeline because this is going this way, so this need 5 inch diameter and all those engineering you need that. So mass balance is the key to any conversion process. key for everything. If in and out you need to know, okay, in every field. To do mass balance, this is the box what I showed. This can be a plant, this can be a fermenter, this can be a pyrolyzer, this can be whatever you say, oven or anything. What are the things coming in and what are the things out? Let us say this is a boiler and you are running boiler on coal or natural gas. Let us say natural gas. So, natural gas pipeline coming here and maybe air you are supplying. Let us forget, you need only those two things in this case. What is coming out? CO2, because this is boiler, you are burning natural gas. What is coming out? CO2 and water. All right. If you have air, then nitrogen, oxygen getting consumed. How will you do material balance in this case? Material balance means what comes out, what goes out, comes in, what goes out. So, methane came, but methane does not go out. So, how will you do material balance here? You are trying to track something, that compound change now. So, how will you do material balance? It is very simple concept, but you have to figure it out how to do that. It's simple accounting, atom economy. So, since compounds are not stable, you will go to atom level. CH4 is coming, no more CH4, but C is coming. C will be here in CO2 or carbon monoxide. So, let us do atomic balance. How much carbon it came, how much carbon gone in CO2 and all. Now, you can do material balance now, right. So, that is why ultimate analysis you need. If you do not know carbon percentage, you can't do material balance. So, once you understood that, it is very simple. Input minus output is accumulation. All right. I put this way, something came out, and if it is not equal, either it is here, am I right? It is accumulated. Input minus output is accumulation. It's with unit time and other things. At a steady state, accumulation is constant. This can fill only this much. After that, it's overflow. Am I right? Initially, you started, it's filled up this level, accumulation, now it's coming out. So, accumulation constant, that is a steady state, so you can say 0. So, in equal 5 kg per hour coming, it should be 5 kg per hour out, maybe in different compounds. So, this is one example. The chemical constituents changes to chemical process. So, natural gas boiler is methane, air is oxygen source, but you have nitrogen also, you have to remember. You get CO2 and water. Now, you have to put a control volume and do material balance, because if you do not know how to do that, how will you design pipeline for how much water vapor will come out? Engineering part of it. How much water will generated, then water pipeline condensation you need to design. CO2, how much CO2 will come out, so you have to design flow rate of that. So, this one example quickly, and you try to see it in the slides. So, we have 1 kilogram reacts with air. Okay. It can be oxygen also, but yesterday I was talking oxy fuel versus normal combustion. So, oxygen has cost, so many boiler run on air. So, air, all the methane is to be consumed. You assume that 100% methane combustion. It may be 99%, 99.5%, but let us assume 100. 30 kilograms of carbon dioxide, water and nitrogen will appear in the product stream, because nitrogen will not take part in combustion. Few will be oxides, but mostly nitrogen. So, if you do not know how it's a boiler, then you have to design pipeline, vents and other things, right. So, you know this CH4, CO2, water and nitrogen. What we don't know, we know 1 kg, all right. So 1 by 16 moles, all right. This much coming we know. We need oxygen, but oxygen comes with nitrogen. So air we can represent O2 plus 0.79% of ratio of nitrogen versus oxygen. So you can write this air formula, and A, we don't know how much air we need, all right. Then CO2 will come out, we don't know how much, that need to be calculated, so X. Water will come out, we don't know how much, so Y. And nitrogen, G, we don't know. Now you do material balance. So what is, how much carbon? 1 by 16, no carbon here, no carbon here, X carbon here. So X is equal to 1 by 16. So you can get how much CO2 came out. This is the simplest one. Once you know carbon turns to CO2, C plus O2, 44 divided by 12 CO2, right? This is the first one. But now start from there, go to hydrogen balance. This is the formula. How much hydrogen? 1 by 16, 4 equal to 2y. So you solve it, y equal to 1 by 8, you moved one step ahead, and now you know how much water because of atom balance, atom economy. Now you go to oxygen, do the same thing. Now we know X and Y both, so you can use that formula and you will get A equal to 1 by 8 moles, so 4 kg of oxygen. Go to get done everything. You should practice in any lab experimental analysis in and out, control volume. That will clear your thoughts, what was coming in, what was going out, kg. That will tell you how much conversion happened, percentage conversion. This is methane and on, there will be sugar and ethanol. You can balance it out. Percentage conversion of sugar to ethanol. You have ethanol this is, you have written the equation, you know equation, put it like that in docs, and it's very, very clear picture it will give you. And if you are not getting in equal to out, then it's sitting in your reactor or some mistake happening. That's the way we should look for all this fundamental, and doing any experimental research you should look that very, very closely. Then you start, now I got a good result. It can be exciting, but when you do this, no, it's not something wrong going on. So cross check with material balance. The next one is energy balance, which many a time not required, but in balance is same math, input minus output equal to accumulation, or if there is a generation, it's okay, it may not, then 0, in equal to out. Here you do enthalpy balance. Your kg becomes more heat now, joules and all. So you do the whole volume and all, not very much required for you at this stage, but the first one is the fermentation. This can be pyrolyzer, this can be gasifier, anything. Carbon conversion, you want to know how much carbon in methane came, how much carbon. This is not useful, this is useful. So you have to see that. There may be another product is charcoal here, then you will know how much carbon gone to charcoal, what is the percentage conversion of carbon into charcoal. So that, how are we doing with time, Bhagwan? Another 15 minutes? Okay. How we go back? Need help? How we escape from there? I need to go to first slide. Oh, I'm here. I forgot that. Yeah, now I can do. Yeah. You just tell me when it to stop, and I will stop it. Okay. Otherwise, it gets longer. We are going back to take biochemical, thermochemical and carbon capture technology. So I say it's not clear boundary. I end up talking many other things which is relevant to other chapters also. So everything we are talking about this graph, 420, 427 is keep going. So carbon neutral we talked, why? So conversion technology, we'll go now pyrolysis, fermentation and other things. So let's do that. So there are three approaches: thermochemical, biochemical and hybrid approach. Thermochemical, temperature, pressure, catalyst, you need to know some reaction engineering concept, how reactions happens. So if you put in that, this is thermochemical approach. So using thermochemical, you can, simplest thing you do, you can burn something. And heat can give you electricity. The next option you have is you can gasify partially biomass, you can gasify. If you want to gasify, you don't want to do combustion. That's easy, you supply excess air, it will burn. But you don't want to do combustion. So we need to cut down oxygen, such that all carbon does not go to carbon dioxide. You want to gasify but don't want to lose energy value. So you will supply limited amount of oxygen, that is called gasification. I will show you want to do that. Pyrolysis, you don't want to go to that high temperature in gas phase, you really want to make liquid out of it. Gas will happen, no matter which process you do, you will get solid, liquid and gas, all three. Even in combustion, solid which is ash or some carbon left over. Gasification you will get all three. Some tarry material will get, some char will get and some gas. Pyrolysis again you will get all, but you want to get oil more here or char more here. So this is typically done thermochemically. This side I have been working, or my group and many others are working, it's called hydrothermal, only because this side requires dry feedstock and drying cost energy. So can we use reaction engineering or water chemistry to see water can do reactions here as a solvent and do. So that part is called hydrothermal, and then we have to look at water at high temperature and pressure. So there are two different phases, subcritical and supercritical. I will come back on that, but using these things again you can make all these products. Chemical conversion, hold on for hydrothermal, which is very similar. So let's look at, if you are looking at a scale, pyrolysis is no air or no oxygen, and combustion is excess oxygen. Okay, how did we put in number? So that is called equivalence ratio. We call it ER. ER is 0. Equivalence ratio is 0. For gasification, equivalence ratio is 0.2 to 0.4, ideally 0.2 to 5 or something like that. For combustion, you want to supply enough oxygen, you make sure everything burns, so when excess oxygen, so greater than 1. Okay? So equivalence ratio is how much oxygen you needed for complete combustion versus how much you supplied. That's equivalence ratio. See, these are the ways to present number and start working in processes, control the ER. Plot it, equivalence ratio of gasification here, pyrolysis is here, gasification is high temperature and excess oxygen. Thermochemical, you have different reactors because you have a high temperature material, so fixed bed reactor, fluidized bed reactor, auger reactor, plasma. So pyrolysis, we'll talk about this. So look at video when you have time, it's very clear. But what is pyrolysis? Not burning. Burning is combustion. Carbonizing, right? Or heating something in absence of air is pyrolysis. Okay, pyrolysis will be no oxygen supply. So there is oxygen in biomass that will try to come out and burn something, because you saw the formula 30-40% oxygen. That will take some carbon with it, some hydrogen with it. All right, oxygen does not come out alone. It is oxidized form is CO2 or water. So it will take some CO2. So when you do pyrolysis, even if you didn't supply oxygen, you will see some CO2 coming out because of inbuilt oxygen. It will see some water coming out because of biomass had it, and then you got the gas phase. Some oil will form and some carbon will be left in the form of carbon. How oil will form, you tell me? Solid, I can imagine, you hit that, you carbonize. Gas, I told you it will come out. How oil will form? Because pyrolysis we do for oil, pyrolysis oil. So how oil forms? Anyone? So what happens when you heat something? So now I gave you enough background. Biomass, what it contains: cellulose, hemicellulose, lignin. These are all polymers. Okay, and then I took you to ultimate and proximate analysis to elemental level. Now you think when you are heating, what happens to cellulose, hemicellulose and lignin? They are polymer. So if you heat polymer, what happens? They will break, right? They will break, melt, all those things will happen. So when they break, depends on how much heat you are doing, right? Faster the heating rate, higher the temperature, they will break more. Okay. Now gas formation is when it's broken completely, it cannot combine back, it's a permanent gas, right? Methane, CO2, water and all, vapor, they are permanent gas, they stay like that. But if you have a bigger molecule, which is still not gas, it cannot stay, basically it's a reactive species, broken down because of temperature, but it is still reactive, it's not gone to gas phase. When you cool it down, what will happen? It will try to go back. There are so many reactive species inside this glass, and they are trying to either go gas or liquid, go gas or solid, but in the end they will start joining, right, because of chemistry at a radical and sun. So when they join together, when you cool it, they drop, it becomes tar or oil, all right. So that's how you get oil formation. So it depends on temperature and heating rate. So you will get oil also. Now you got a system where you can produce oil, you can produce gas, and you can produce char. What we need to produce, we need to know. This is a municipal solid waste and we are happy with some char and put in ground and lawn, we need more char. This is a fuel industry and we want to make diesel or gasoline. We need to tune such a way we get more oil. Okay? And gas has almost no value here because it's low temperature. If you go higher temperature, then you get better gas quality. Okay, so that's what is the pyrolysis. This is the last slide. Okay. So pyrolysis, tuning, I said that. If you are trying to make oil, you want to do fast pyrolysis. It will give you up to 60 to 70 oil because it gives so fast heating. Imagine 200 degrees Celsius in 10 seconds. So 400 degrees Celsius pyrolysis temperature is typical 400, 500. So if you can heat in 10 seconds, then it breaks down so fast, but then cools so fast, it get more oil. Okay, so if you are looking at for fuel, liquid fuel, do fast pyrolysis. Typical time is 10 seconds, 2 seconds, 5 seconds in seconds. And then you will have some char. So you will see less char. If you are trying to balance both, do the heating rate little slower but not very slow. You will get all three. If you are trying to do in between completely, there is in between, it's not given here, but if you are trying to go slow just for char, then go for slow pyrolysis. It will carbonize more and it will make more char. Said gasification also, you will get some char and other things, but gasification is done for making gases. Okay, so you will see 85% gases, less char and oil. I will stop here, let's take break and I will continue from here. Okay. Okay, yeah, that's good. What time you are meeting again? 2:30.
Thank you so much, sir, for your talk. It was really nice. Let's move for lunch. There's one announcement that we regret to inform the golf cart is not available today. So all the Central University of Rajasthan students, they have to walk and go to the guest house. And for the external students, we have arranged a car, so you can wait outside the department and the car will take you to the guest house. And another thing that I request all of you to come back at 2:30 sharp so that we can start again with the lectures. Thank you.
So
Hello.
Hello. Hello.
Everyone please occupy seats in the center. I hope everyone is settled. So let's begin with the sessions. I request Professor Sandeep Kumar to continue with the session.
Okay, so good afternoon, everyone. So I hope you had a nice break and questions for me. Could you think something from last session? We started discussing thermochemical and biochemical conversion processes. Hello. Yeah. So any questions? So let me go off topic a bit, and then I will say if you are looking for higher study and if you are looking for masters, requirements are different than if you are looking for PhD. Okay. Masters, many people go self-funded also. Okay, and I will bring to the reality. It's very difficult to get funded masters in US. You will get it. Many people get it. One of my students got it, but many of my students didn't get it. So if you are looking for masters and funded masters, you have to be selective how to go for that. If you are looking for PhD, many university have two kind of PhD. One, you can go direct PhD just from BS to PhD. Okay. Some university ask for masters then PhD. Okay, so that's the two different routes you can take. So when you are applying, you have to look at the guidelines, what they were, what kind of offer they do, and never be shy of emailing graduate program director of that department. Okay, that's the best resource you have. Whoever is there, they will respond to you. Okay, so look at the website, look at graduate program director name, and write to that professor. So that will be very helpful, and they can say that whether TA, there are two kind of funding you can get. One is RA, research assistantship, is called GRA, graduate research assistantship. The other one is called GTA, graduate teaching assistantship. So teaching assistantship is something paid by department. So let's say I'm teaching a course and I have 50 students. So it's very difficult to do all grading and homework for me for 50 students. So to support, department hires TA, teaching assistants, and they are paid equally like RA. Okay. So if department has TA need, they will take. Okay. If they don't have TA need, then you have to depend on RA if you have RA on. So that's one option you should be looking at, GTA or GRA option. So master, many of students I've seen, they go self-funded. It depends on what's the background, how much you can afford. But they go self-funded, but they find options when they are in campus. Okay, sometimes they get a library, some other department, and they help on those things. So that's also a possibility. But that's also a risk, how much you want to take that. Okay, most of the time they get it. Okay. But something to think about. For PhD, self-funded, I will say not a good option. You won't survive that much dollar expenses. Okay, so if you get a PhD, basically you want to be funded, and when you get funding, PhD fees are waived. Okay, so you don't pay any fee. In master, even if you are funded, many universities they will ask you to pay in-state tuition or 1/3 of it. So your stipend and tuition becomes neck to neck, so you don't have much margin. So going for just master is little costly option, and depends on background. Some families can take that, some families is difficult, some students cannot, difficult. But PhD, if you are looking for that, look accordingly. So do TOEFL or IELTS, English test is must. That's the discussion starting point. Look for application method and other things, RECO, and start interacting with graduate program director. Other thing you want to look at is what kind of university you want to go. There are 4,000 or more universities there. Okay, so location also becomes important. Some part of US is very good, nice. You like very similar to here where I live. Weather is very similar to here. We have all 4 seasons. Some part of US is very different, 6 month cold, very cold. Some parts is very hot. Okay, so you need to look at it where you want to be. Okay, and that's also a good criteria. Once you go and then you start seeing it's a surprise. Okay, so when you choose university, give attention to that. There are many good university in Midwest, Mid-East area and other things, but there are not many big cities around, many not big industry around. So those kind of things matter. So be choosy on university selection also, which state you want to go, West Coast, East Coast, Texas versus New Jersey, all those things matters, okay? And again, definitely if you are emailing, be careful or emailing, be specific, don't overload with information. Too much. Many a time people read on phone nowadays, am I right? Some email and quickly. So if it is overloaded, you will wait to go to the computer and then it might go. So start a simple discussion and then build on that. Okay. I hope it's helpful, and then let's come back to what we have been discussing. Conversion technology, and we were talking about, where did we leave? One of you. Pyrolysis. Okay. It's got disconnected. Oh, this was another. So again, feedstock we are talking is very complex. It's not straightforward. It's a mixture of aromatic compounds, sugar, carbohydrates, protein compounds, so nitrogen, sulfur, carbon, many things are there. And again, I said that this is cellulose, this is hemicellulose, this is lignin, all mixed together. If you want to make ethanol biochemically, you are looking at this and this. You cannot ferment this, all right? So what we do with this, how we separate, all these things matters in biochemical. So thermochemical conversion processes, I was talking combustion, gasification, pyrolysis, torrefaction, and hydrolysis, am I right? So let's say pyrolysis we talked about, you have a different heat temperature and you will get all three, and how to tune it, you will get oil and other things. So we'll come back on that. But if you want to do biochemical, you want to utilize sugars for alcohol, am I right? And we are not talking a starch, we are talking cellulose now. So how will you reach to sugar here, carbs, when lignin is protecting? How will you reach there? Any thoughts? You designed some enzyme which will break down cellulose, okay? It will do fantastic. You know that enzyme is good. But how will you subject to that? How will you make sure enzyme reaches to cellulosic sites? What idea you have? Let's say you got sawdust, wood dust, and you want to do enzymatic hydrolysis. So how will you make enzymes accessible to cellulosic sites? What we need to do? If you put as it is, sawdust and enzyme and in your medium and all, will it work? Will it work? No, because lignin is a barrier and it's not going to allow you to reach there. So you have to deconstruct it, you have to treat it, you have to break it down, somehow do that. The paper industry does pulping. So something you have to do, that's called pre-treatment. And pre-treatment is exposing sugar, increasing surface area that enzymes can see that, they can do that. So now doing this is a cost center. All right, you are going to add cost in using pre-treatment process. Pre-treatment can be chemical, physical, or you can just grind it and all, a combination of those also. And once you did that, then you have sugars, you can do fermentation and also. So if you compare biochemical versus chemical, thermochemical processes, we already talked what the gain you have. One is low temperature, another is high temperature. Okay. One is microbial process, another is thermal chemical catalytic process. Okay. So both are using catalyst. Right. Thermochemistry, if you are doing, you are using catalyst here to expedite the reactions and save the temperature. In biochemical also you are using enzyme as a catalyst, a biocatalyst. So you need catalysts understanding how they work, how they reach to sites, how efficient they are. Time wise you are dealing with different timeline. One is hours, days, another is seconds, minutes. Efficiency wise that is moderate. This is better efficient because it's faster. But purity wise you might get purer compound here because you are not disturbing too much. It's not breaking everything. End products, biogas, ethanol, butanol, same thing. We talked about, just summarizing, for biochemical composition analysis is important. How much? That's how you will know that how much carb can go to sugar and other things. And thermochemical proximate analysis, ultimate analysis are more important. Then definitely physical characteristics, how easily you can grind, pelletize, heating value and other things. Anaerobic digestion, right? We know very well, most of you know very well. What happens here? There are two kinds of setup, aerobic or anaerobic, okay? If you have organic matter and aerobic condition, what product you are going to get? CO2 and water aerobically outside, all right? That's a stable product, it's fully oxidized product. If you are doing anaerobically, you have microbes, but you are going to get methane and CO2 mixture, okay? And some unstable products and some sulfurs. So these are pretty basic, I'm just moving out. What are the aerobic and decomposition, anaerobic decomposition? You all know more. Are you familiar with this growth curve? All right, cell growth, so lag phase and exponential growth phase and all. Fermentation we talked about, how we do that. So sucrose, we have glucose plus fructose, so sugarcane juice and all, but fermentation we talked. Okay, so here's the thing. What enzyme is used for cellulosic material? Not a starch. So typically it's called cellulase, okay? And it's a mixture, it's a cocktail. And then for hemi, you need another cocktail, hemicellulose. So enzyme cost becomes efficient. So to save enzyme cost, what option you have? So there are two things. One is pre-treatment, second step is enzymatic hydrolysis. Are they independent? Are they independent or they depend on each other? If you do very good pre-treatment, enzymes will be more effective. Effective means faster, less enzyme, all right, so you save cost. But for doing very good pre-treatment, you are putting energy, chemicals, because pre-treatment can be chemical pre-treatment, steam pre-treatment, or grinding. If you don't do very good pre-treatment, then you need more enzyme to do that. So they are not independent. Okay, you need to balance how much we want to do. And that's together makes big component of the cost. So you have enzyme cost and pre-treatment cost. If you join together, 40% of the cost, operating cost, goes in that. Through our research contribution, can you start reducing that? Okay, that will be more impactful. It's a cocktail of enzymes, so you have to ferment all sugars, otherwise you are losing. Already you have, how much sugar you have in cellulosic biomass? Hemi and cellulose together is 65, 60, 70% together, am I right? So you are already 30% less, some other material. Out of that, 60, 65%, these are all mixture of sugar. If you don't ferment, our efficiency will go further down. We'll losing that. It's all material balance. And fermenting all kind of sugar is tough on enzymes, means how good efficiency. So that's a challenge. If we do pre-treatment, like alkali treatment or acidic treatment, we end up generating some byproducts which might be toxic to enzymes. It will slow down. That's another challenge. So resistant to toxic material from pre-treatment, like you might end up glucose derivative HMF. Okay, glucose will break down to HMH, HMH becomes inhibitory. Xylose will break down to furfural and furfural becomes inhibitory. So you need to minimize this toxic material during pre-treatment. Robust and able to compete contaminant microorganisms. So you need thermotolerant, ethanol tolerant, that's another in fermentation, product inhibition, pH tolerant, high fermentation rate, minimum metabolic other products. So these are the challenges makes tough in biochemical. There are different approach for fermentation, especially in ethanol. Separate hydrolysis and fermentation. So you have a enzymatic hydrolysis and then fermentation. You can have simultaneous saccharification and fermentation in one. Okay? You can have a simultaneous saccharification and co-fermentation, 5 sugar and 6 go together. Or consolidated by processing, one chamber and do everything. So these are the different options you have. Technical barrier which industry is facing, especially when we are looking at corn stover, grass, rice husk, another thing. Feedstock valuation and delivery. Analytical method, which I have been talking, it's all becomes tough. Supply system, which we don't see, that's another logistic issue. Soil sustainability. If we dedicated crop we grow, how sustainable it could be. Biomass recalcitrance to conversion. Recalcitrance means difficult to reach to the site, it does not want to change. For that we break down using chemicals, and that's pre-treatment, hydrolysis and fermentation, how easily we can do. Process integration. So what are the different things you are handling in this plant? Solid, which is biomass, and I told you this solid is different than coal. It's fluffy, bulky, it makes bridges, you fly it, all right? Coal is different solid, which is high density, flows well, so that's a challenge, solid. Solid liquid separation. If you put water and biomass, what happens? Does it mix well? Immediately weighting problem, it does not weight well, and then you have to do that. So that's all problem. Process chemistry is very, very complex, especially lignin. I don't know how many of you study lignin. Lignin chemistry is well known for being complex because you saw the structure. 3 monomers, aromatics join in many different ways, many different, so it becomes very difficult. So carbohydrates, if you heat it, it will decompose by 575 degrees Celsius, so all will be gone, volatiles and all those things. Lignin decomposition starts from 150 degree, it continues here for different temperatures, so it has a kind of consistent weight loss. So you cannot say, but carbonyl, you know at what temperature it will go in TGA. So it's a very different. So lignin chemistry makes it more complex. So process chemistry. So now I'm bringing, again I say corn, starch, potato, wheat, cereal are easy to ferment. You will see a lot of ethanol industry doing that, sugar cane doing that. But we are talking this kind of things. Okay, and I'm showing how this is different than starch. So corn process or sugar cane process. If let's see if you have a sugar cane juice, what the process will look like if you want to make ethanol. You get sugar cane juice, ferment it because it's almost ready, sucrose or glucose. Okay, ferment, distill, dry ethanol. Let's say you have a starch, corn stover or something. If you have a starch, then a starch you need to cook, make it softer, bring in solution, basically hydrolyze. This is again commercially known, so this is easy to do, but you added one step, cooking of a starch. And then remaining process remains same. The enzyme is alpha amylase and glucoamylase enzymes, okay? Now, if you are adding cellulosic process, grass, what's why I'm showing, or wood, what you added here, started from cellulose. You need to reach these things to get cellulose, okay? So you need to do pre-treatment, all right? So pre-treatment you can do thermochemical process, use alkali or acid or something like that. So when you do that, you get cellulose, you do hydrolysis, and then you take the same route. But you generated another product which is lignin, and that needs for heat recovery. So this is extra, and we want to get ethanol at the same price at corn or sugar cane. So we depend on all of us how good we can do this, so save the cost and match the price. Okay, so these are the challenges, good to take on. Here the enzymes are different, it's costly. Pre-treatment have multiple options. Pre-treatment depends on enzymatic hydrolysis method, which one you take. So what pre-treatment does? It breaks down, somehow you expose it. The fibers are hidden, now you expose it, broke it down by temperature or by grinding or by chemicals or whatever way. So the only objective of pre-treatment was enhance the rate of hydrolysis or enzymes efficiency and the yield of sugar, because sugar will go for fermentation. So pre-treatment can be physical, physiochemical or chemical. If you grind well enough, grinding will increase surface area, am I right? Surface area means it exposes more of this. You can do that, but this is power intensive. All right, grinding is, see that we run grinders at home, is kind of, we quickly switch it off, it's taking too much electricity, am I right? So it's like that. You can do irrigation. Physiochemical, you can do a steam explosion. So exposed to steam and with that, it will open up, it's basically swells and do that. sulfur or CO2, ammonia fiber explosion, supercritical CO2, these have been tested one. In chemical, which we know more, know how to do chemical treatments. So you can use acid, alkali, organic solvents, ionic liquid, hydrothermal, which I was talking. In general, alkaline reagents have high selectivity for reaction with lignin over carbohydrates. If you are using alkali, it's like pulping process, paper making process. They use a lot of alkali. So it breaks down lignin, it goes in black liquor, and you get the carbon fiber, cellulosic fiber. Acidic will hydrolyze hemicellulose. Okay, so you see hemicellulose, it will hydrolyze and it will open up. So this is takeaway message. Higher pH, what will happen? Dilute acid will remove hemicellulose. So we should know if you are using acid, what's going to happen. You expect more hemicellulose in the solution, and you don't want to lose sugar, but it is in solution, so you have to take this and other side also. Control pH, hot water treatment we do. Add pH constant or buffer. You can do pre-treatment here also, but it will remove part of lignin, part of hydrogen. This is Callinan balance. You can go fully alkaline, and it will remove most of lignin. So these are the methods you can do that. So pre-treatment, I already talked it, but cellulose accessibility, that's what we need. Low capital cost and low pressure system we want. Am I right? Low energy cost, low degradation. There is another way, microbial fuel cell, many of you are working. So you can do that. Torrefaction. What is torrefaction? Have you heard about this name, torrefaction? So if you do pyrolysis, you can change into oil, char and all. And let's say your biomass is 100 kilometers away, and you want to bring it to the pyrolysis plant. And what option we have? We talked yesterday that if you transport as it is, it will be more water, dust and other things. It's a bulky material. So one of the way is called pre-treatment, is torrefy it a bit. Again, it's energy, heating value, how much you are bringing. If you torrefy and pelletize, it will have a more energy in given unit volume. Okay. So torrefaction is roasting of biomass. It's like a coffee roasting we do. So basically roasting of biomass, basically pyrolysis at very low temperature, 200 or something. So what it does, if you roast biomass at 200 or so, what will happen? Some volatiles will come out, am I right? And it will clear pores also when it comes out. So volatile gone, so it becomes fluffy, more porous. Now you can compact it, make pellet nicely. So energy density will be higher. I think I'm missing some slides. Just give me a moment. Can you put this up? Suddenly I was seeing the biochemical, so good that we covered biochemical. So pyrolysis products depends on what kind of feedstock, and we are talking there are three different things you can make: oil, char and gas, and it depends on different composition, temperature, pressure, vapor residence time, particle size and heating rate. Okay, so now if you are looking at bio oil or pyrolysis oil, if you are doing pyrolysis, you will get to bio oil which has a moisture content of 15 to 30%. What is the heating value here? 16 to 19. You compare heavy fuel oil is 40. So we pyrolyze something to make oil, right? We expected to have heating value closer to oil, and take any pyrolysis oil, you will get 20, 16 and all. So why we should do this? It turned to liquid, but it's no way close to what we want. So why we do that? What benefit we get doing pyrolysis if we are making oil? Anyone? If we do pyrolysis, we want to produce oil and the oil quality is still inferior. The quality is directly linked with heating value, which is still biomass. What is the heating value? 15, 16, 17, and oil we get is almost similar. So what we did, why we do? Yeah, so that's fine, but take a drum, okay, and put biomass. Biomass we know is 15, 16 megajoule per kg, but one drum of biomass, how much energy you will have? Let's say in a drum you have 40 kg, so how much energy you will carry in a drum? Now same drum, take this pyrolysis oil and put, how much oil you can fill it up? Much more energy than this. So even though heating value was energy density per unit volume increase, per unit mass is same, so it can confuse. But now you need to say that we wanted to turn solid to liquid, which is easier to handle, easier to store, and then you can easier to do upgradation. Upgradation means from here to here we can do now, it's a liquid reaction, liquid, 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 gas, something like that. It's not solid, okay? And we remember biomass is hydrogen deficient. So this is hydrogen deficient still, we didn't add hydrogen yet. But now you can conduct hydrogenation process to upgrade this. So that's why we make pyrolysis soil is one of the option is the intermediate process turn into liquid and then go further. So biomass we did pyrolysis, you get oil. Now this is a stabilization and upgrading which I am talking. If you are doing fast pyrolysis, the products are unstable. You cooled it out, but if you store 2 months, it will change. So you need to stabilize, you need to remove water, phase separate or water way, and then upgrade, or you just burn it, electricity or upgrade. The concept what we are talking, that economy of a scale, we can think of a centralized facility, and at this facility if you are bringing biomass, it's tough, but if you are bringing oil from here to here centralized and then you upgrade it, then it's better, am I right? So we can think of a mobile pyrolysis unit. We have a pyrolysis unit built on a truck or of that size and goes to a forest or wherever, take biochar, make oil and char, and then it brings to the centralized facility and do reactions like refineries, and you can make it. So that concept might be more suitable than bringing solid as it is and then do that. So fast pyrolysis has advantages. Atmospheric pressure, modest temperature, most of the pyrolysis are done at 450, 500 in that range. Disadvantage, high oxygen still I talked, oil has low heating value, that means low pH, it becomes acidic, crude oil is not acidic, water content, phase separation is not stable, different kind of pyrolyzer you can use. Okay. So fluidized, circulating fluidized, rotating, ablative, vacuum, different kind of reactor you can make. How many of you know fluidization? Fluidized reactor. Fluidized. Circulating fluidized bed reactor. What is fluidization? That comes. So think of wood, a drum load of wood, and say that this is pyrolyzer. So you start heating, but will this heat will be uniform inside the drum? Will it be? Let us say this is pyrolyzer. Fill the drum. Now you are heating outside, and this can be this big or much bigger, am I right? You see the industrial scale, this is not lab scale. So now you have lot of wood, big diameter, and you are heating outside. Will that heat will be effective, uniformly distributed? It will take time, am I right? The surface will be heating faster, then there will be gradient. To become uniform, it will take time. By the time property will change, reactions will change. So it's a heat transfer problem. All right. So how you transfer heat? We know things, if you mix well, even in cooking, it's nice heat distribution. Mixing does mass transfer and heat transfer both easier. All right. And here if you are putting this, there is no way to mix wood chips. You can tumble it, right, but you cannot put a stirrer and mix it. So what option we have? So again, coal industry is called fluidization. So you put sawdust, wood dust here in this, and pass nitrogen or any gas. In pyrolysis, you don't want to pass oxygen or air, because pyrolysis is done in absence of that. So you pass some inert gas, and you have filled with dust, wood, sawdust, or very fine biomass, and from bottom you pass. What will happen? The dust will try to rise. If it's too much velocity, it will come out if it is open, and if it is right velocity, it will look like boiling. All right, just like that. It won't go up, and it may not be settling. And that's the right time is called fluidization. You made like a fluid-like behavior. Okay. not exactly liquid, not exactly gas or solid, it's fluid kind of things, it's nice mixing and all. So that's how you do pyrolysis in fluidized bed. Coal industry does day in day out, they know how to do that. So these reactors are bubbling fluidized, means you bubble it and it comes down, or circulating fluidized bed. So you can circulate. So there are different design, but my point is it's not easy to heat biomass just like that. You need some mixing, so it's done through fluidization. And you need these are the barrier: dry, high oil content, improving boil. We talked about that. Oil you produce is low heating value, high oxygen content. I talked about this. So how you make to liquid fuel? Let's say you want to make diesel. You got bio oil. Now you want to make it to diesel. How will you turn? So you get bio oil here. This is pyrolyzer, fluidized bed or whatever. You get bio oil, phase separate, some lignin will come out, and then you add hydrogen. It's a hydrogenation process. Remember, biomass is hydrogen deficient. At certain stage, you have to have CH2 ratio, H2:1. So that's how you put hydrogen, catalyst, and temperature 200, 300 range, and you will get oil which can be distilled and fractionated. So that's why hydrocracking of bio oil, you can say that. You can gasify and then run Fischer-Tropsch reaction, catalytic reaction, you can do that. So that's what why we make pyrolysis for bio oil, liquid. You have to make bio oil first and then do hydrogenation process. And through pyrolysis you can make diesel, and it has been shown to that. The challenges is cost, how efficiently you can do that. Combustion I already talked. You can have a direct combustion, or you can have a co-firing. And last lecture I was talking about what is the challenge of co-firing. Right? It does not mix well. So if you have a boiler and you are doing direct co-firing, boiler need to be changed a bit, right? So you cannot have a single line, you can have two entry separate. You cannot mix because it won't mix well with biomass. Or indirect you have separate. Or you can have two parallel, one is biomass, one this. Advantages of co-firing. Coal has a lot of sulfur, biomass has low sulfur. Power plants struggle how to keep sulfur down. So you can mix biomass, it will bring sulfur down, it's math, all right? Coal versus biomass I talked, so let's leave it. Gasification. So pyrolysis you have a good understanding now. If you are looking for bio oil, you can make it. Okay, if you want to make char, just heat at low temperature and you can get it. Gasification, what it does? If you have a biomass, you can gasify at 700, 800, 900 degrees Celsius, supply limited amount of oxygen, and the mixture will come out is called syngas, which is a carbon monoxide and hydrogen. And this gas has high potential for making different chemicals. You can run gas turbine also, it has energy, electricity, or you can do Fischer-Tropsch reaction and one carbon and hydrogen. What is oil? CH2CH. Okay? So Fischer-Tropsch, they came with the solution that you can build the chain, carbon, hydrogen, and it carbon. Okay? So you can do Fischer-Tropsch reaction, you can get diesel. Water gas shift reaction, you can make hydrogen, methanol. So all these chemicals you can make from syngas, and if you do biomass gasification, you get syngas, and then you can turn it. So that's the advantage of gasification. And there are different types of gasifier, you can leave it. Technical barrier in gasification. When you do gasification, what happens? Tar. which was part of pyrolysis soil, you are looking for bio oil. Now you are going higher temperature, you want gas, but there will be some time. Now it's unwanted. This is wanted, now this is unwanted. That's a challenge. Ash melting, we are talking 800, 900 degrees Celsius. So ash, which is sodium, potassium, silica, they will fuse together, and in gasifier they will make clinkers and other thing, and they will destroy. Low heating value of gas, feedstock, gas cleaning is needed because tar will come and many other things comes. So this is Fischer-Tropsch reaction. One, you got carbon monoxide and hydrogen. You run at temperature and catalyst, and it forms alkanes. Okay, it's a loop. So this is how you can make it. This is from German scientists, and they developed when we are looking for coal to liquid and to how to make this. So coal gasification you can do gases, and that was developed for that. But now this can be applicable to biomass gasification also. But here you need very clean gas. Otherwise, this is a catalytic process, it will poison the catalyst. So this is typically done at 300 degrees Celsius under little pressure, and the catalyst can be different catalyst, cobalt, iron, but this process is commercially done. Okay. Coal liquefaction and making Fischer-Tropsch, you get diesel. Sasol is one company in South Africa, they do coal liquefaction and coal to liquid basically. So this is well known process, not done much for biomass. And this one we talked anyway. This one we just finished. My slides got mixed, looks like. Okay. Biodiesel. If you have oil, lipids, okay, you can make fuel out of it. The compound which is called fatty acid methyl ester, its fame is basically biodiesel. So let's say you have vegetable oil, put in an engine, can you run it? Oil will burn or not? Burn, am I right? But it is, if you have diesel and oil, if you compare, which flows better? Viscosity is higher in case of oil, am I right? You can turn into biodiesel, its viscosity is less. That's the challenge. So soot formation and other things is not that. So that viscosity, how you remove it to make it biodiesel. So these are fatty acids chain. You do trans-esterification, triglyceride. So 3 fatty acid and this glycerin backbone, this is giving you viscosity. Can we cut it off? Then it becomes a straight chain and it's no viscosity or very low viscosity, and then it's fine. So this is what is done with alcohol, methanol and catalyst, potassium hydroxide, and you can make biodiesel. It is very easy to make. You can do in very easily, low temperature, methanol and sodium hydroxide, fatty methyl ester, and you get glycerol. Glycerol is a byproduct of this. Okay. Now, this is giving you another product. How can you develop for this one? This is not very clean glycerin because you have methanol and acid contaminated, but this is another potential. You can make hydrogen out of it or use in soap and many other things. Okay. Again, material balance, how much you put, how much you get. Now coming to this, this is what I wanted to come. So you have oil and methanol, you get glycerol and biodiesel, and this is blend fuel. All right. Blend fuel means you have to mix with diesel. We are looking for drop-in fuel. This one is solving some problem, not entirely. We are looking for drop-in fuel. So can we take this and turn into diesel, or let's call it a renewable diesel or green diesel, not biodiesel. Yes, we can do that, and remember it is hydrogen deficient. So put hydrogen catalyst 300 degrees Celsius around that, and you can turn it like a diesel, a straight chain. That is called renewable diesel. There are many companies. UOP is one well-known company. They take lot of grease, food. Yeah, these are diesel basically. R1 means long chain, H2, H3. This is end, so H3 in the chain it will be 2. So now this is your drop-in, and this is being done. UOP is one company. There are few in Europe. They are taking all kind of chicken waste, those what we call leave. So your feedstock is too different. In pyrolysis we are taking biomass. Yeah.
Once we go for pyrolysis, getting oil, and then we are converting it to hydrogen.
Yeah.
Another case we are going for biodiesel, and then again going for this catalyst and
No, so that's what I'm saying. We are mixing. What you are talking, if you have a biomass, then we can compare between pyrolysis and gasification. Okay? But if you have oil already, vegetable oil, so grease, used oil, cooked waste cooking oil, then fats, chicken fats, lot of fats we get, we throw it. Those are oily, those are fatty acid kind of thing. They are like this. These are oil, not cellulose or fibers. So these are used for making biodiesel. But what I am saying, those are blend fuel. World is looking for drop-in fuel. So those things can be done commercially by adding hydrogen catalyst, and 200, 300, 350 is a proprietary for different company. They are doing that's a hydrofining process they call it. They have their own name, but the basic chemistry is adding hydrogen catalyst and temperature, and you can make a straight chain diesel. And that is a renewable diesel. This is tested and it is done. Okay. So now another topic will come. Let's see. So we covered biochemical quickly, fermentation and enzyme. We covered pyrolysis. We covered gasification quickly. We covered biodiesel and renewable diesel. Each one can take hours and maybe days to go deeper, but this is the fundamental level I am giving. Another one process is called hydrothermal process. Remember thermochemical, biochemical, and I put hydrothermal also. Hydrothermal is basically thermochemical, but it is done in presence of water. So water was not wanted for pyrolysis gasification. Here water becomes your part of solvent and chemistry, so you don't have to dry. So hydrothermal process, you can do hydrothermal liquefaction. So you take water as it is and entire feed, put in a pressure cooker, kind of a closed vessel, and heat it, it will liquefy and you can turn into crude. So then you can separate water and crude. So hydrothermal word comes from sub and supercritical water. Okay, combined we call hydrothermal. Hydro from water and thermal is temperature. So what is critical point? Subcritical, supercritical. So critical point of water is 374 degrees Celsius. Okay. At that temperature, there is no difference between liquid and gas phase. They are well mixed phase. Okay, beyond critical point. This phase is called supercritical phase. Okay. Below this liquid or gaseous phase we have separation, but critical phase, no matter how much you can do, you cannot liquefy. It's a single phase. Okay. So if you are working below the critical point, is called subcritical water. That means below 374 degrees Celsius under pressure is called subcritical. Above 374 under pressure is called supercritical. Okay? Boiling point is here, triple point is here. I am talking critical point. So imagine you have water in a container and snow cover. You heat it, what happens? Steam gone. Put a cover and keep heating. What will happen? That's pressure cooker basically. All right, but keep pressure. Pressure cooker is still a low pressure. You can keep building thicker vessel. So what will happen? Vapor beginning, but they are condensing back. So you have mostly liquid phase. Think of water at 200 degrees Celsius and still liquid. Can you imagine? If you don't pressurize it, it's a steam or vapor, but if you pressurize, you will be more liquid phase. Okay? So liquid phase reactions go in reaction engineering. Liquid phase reaction you can do here better contact. So subcritical water you will see more of a water phase and you are doing reactions here. If you go above 374, now water is a very well mixed homogeneous mixture where you have a vapor and liquid phase, not separation. No matter how much pressure you do, you cannot liquefy now this above 374. So these things does wonder for chemical reactions here. You have some salt and put here cold water, salt. What happens to salt? If you put salt here in water, what will happen? It dissolves, am I right? Put some dust or biomass, cold water, what will happen? It will take time to get wet and other things, am I right? In subcritical phase or supercritical phase, you put salt here and here, it will precipitate, it won't dissolve. It does opposite. But if you put some oil, put oil here, it will float, here it will be well mixed. Okay, it becomes better solvent. So this is dielectric constant of water. Okay, dielectric constant, to simplify, it gives you solvent property. Okay, lower dielectric constant versus higher dielectric constant. Lower is more non-polar, higher is more polar. So if you do hydrothermal process, sub or supercritical critical water process, you start heating temperature under high pressure, because pressure is constant, otherwise it will be steam. What will happen? Dielectric constant starts coming down. When you start at ambient temperature, it is about 78 or 80. Okay? If water comes to 200 degree at temperature and pressure, it acts like methanol. What you can do with methanol? Methanol is a solvent, am I right? Wipe it, it cleans. Water at that temperature is very much like methanol. So what methanol could do, it can do. So sometimes you will see that people are using biodiesel production using subcritical water, because it becomes green solvent. Go higher temperature, is as good as acetone, dichloromethane, supercritical, very low dielectric constant, it's very good solvent like hexane and all. So remember one thing in solvent is what time? Just 2 minutes. Okay. So I am coming. So how long is that meeting?
15-20 minutes. I will engage them.
Okay. Okay. So I need to go for a meeting, quick meeting. Okay. So give me 10-minute break and then we have that. You will continue. So where do I go?
Sir, we do the same. Right. So, good afternoon. Now this is my turn to have some glance on waste materials because so I'm also working. हो जाएगा ना? And which we are treating as waste has the most potential and which can as a resource for our future generations. Currently we are considering it as waste, but it is really having so much of potential which can be converted, like sir also discussing about conversion processes, thermochemical conversion, biological conversion, where we can convert different degradable, non-degradable waste into useful products like carbon or chemicals or gaseous components, right? So they have their own applications. So I am going to concentrate only on specific waste where we can convert it into a valuable material. So that is biomass wood material. So in this wood, like explained, we are having the cell wall basically contains cellulose, hemicellulose and lignin. Then he has explained about cellulose, where it is going to process and how we can convert this cellulosic waste. It's basically cellulose is having so many applications. Even waste which is appearing in the nature, that can also have their own applications. So cellulose is like well known material which can directly used in different processes. So cellulose and lignin. So lignin, now we are going to discuss about the part of lignin. I am going to completely non-biodegradable. Then what we can do with that, and where this lignin manage, and what we need to worry about the lignin. So that is the first concept. So from last 2 days we are discussing about waste, but what is the need of discussion about this waste? Why we need these type of waste materials? First thing, the resource availability is getting reduced, and second thing, our population is getting increased, so we need to meet the requirement of our population. So for that purpose we need to have an alternative material where we can feed, right? So today I am going to discuss, so this is tutorial, we will have some lab session as well. So I will first I will give you glance on the material where it is going to be useful, and as I prepared here already, sir has covered all the characterization methods. So he has covered proximate analysis and ultimate analysis. So I am not going to cover those topics again, and just I will throw glance this instrumental analysis. So sir has already given some AST methodology where we can do characterization of specific components or specificity or the specific analysis, as well physical as well chemical analysis of the component. But here some of the instruments which will help us to identify in both ways, qualitatively as well as quantitatively. So why we need to bother about both the things in case of this waste valorization? So as I said, lignin, composition of this lignin is going to differ based on the plant materials. So if we select, it may contain different proportions. If we consider the wood material, then the lignin proportion is going to get increased. So likewise, the proportion will increase and decrease depending on the wood material or the biomass which we are utilizing, which we are planning to process. So when we value added materials, their quality will decide where this particular component is applicable. Depending. So as we know, cellulose, depending on the quality of cellulose, we have so many applications, right? So it will be useful in the food industry, pulp paper and pulp industries, right? So based on the structural group and nature of the material, we will decide where we can apply this material and how much quantity we can use for different categories. So it may be applicable for agriculture purpose, it may be applicable for food grade purpose, or it may be applicable for material purpose. So we have vast area of applications, but that is going to depend on the character. That will decide by the character such as proximate analysis and ultimate analysis as well as instrumental analysis. So here instrumental analysis will give you the pure form, purity as well as quantity of that particular materials. So, and all these things are already covered. Now I will only pectin. Have you heard about pectin? Morning one of my student has mentioned about she is working on pectin and something she is doing. So have you heard about pectin? How many of you like eating jams? How many of we use jam, bread jam? Where we are getting from? It will be in the jelly form or solid form, right? So ever you think about that solid material, where it is coming from or what is that solid material? That basic material is pectin. So here sometimes they will use pectin or it may altered by silica, but pectin will be the food grade material which will have the healthier nature. Because this pectin is inert material as well as it has some beautiful characterization, those characters also will discuss. So those characters helping pectin to use in the food grade applications. So all the gelatinous materials will be prepared with the help of pectin base. So now where we will get this pectin, how we can produce this pectin. First suppose in case of food grain, we cultivate the food grain and will get and will feed our country people, right? Then what about pectin, where it is going to come from? As I mentioned, each cell wall will contain cellulose, hemicellulose and lignin. Pectin is a part of this lignin portion. So as sir said, 20, 30, 40%, like he has already categorized cellulose, hemicellulose and lignin. And in lignin part, some portion will occupy with the pectin composition. So that is the composition where it is readily available and where we can extract. So then what is the status of this pectin in India? Are we really, and as we already know, our country basically depending on agriculture. So we have massive cultivation, massive production. Then what about pectin? And now we are able to even export the pectins to the different nations. Then what is the status of pectin? The unfortunate situation is whichever pectin we are using, almost more than 90% of pectin we are importing from the other nations like Japan, China, USA. So these are the major exporters and the major portion is going to get occupied by China. So all of sudden, if China tomorrow, if they ban export of this pectin, then where we will get all the jam materials or cake materials? So we need to think about this. So in this way, we can we can develop our R&D and we can try to produce there is no need of production. The need of the need of the research is how we can extract these pectin in edible form. So that is the major concern, because pectin is readily available in the different type of waste. So, and what about we are having vast agriculture and we are not able to produce the pectin, then what about other nations? They are exporting, they are at the level to export. How this imbalance is happening? What is the reason? Because there is so much gap. Our population is very high, our production, we are meeting all food grain materials up to the level, and even we are in the export level for other food grain materials. But in case of pectin, we are not able to produce, we are not able to feed to our country, and we are continuously depending on others. So what might be the lacking or the gap between these two different production states? What might be the reason here? And the pectin which we are the extracting is majorly from the fruit waste materials. So basically lignin fruit, lemon fruit materials, and apple fruit, which becomes after making juice. So whichever waste comes out, so that waste they are processing for the extraction of pectin. So that is the basic extraction or raw material which will be which is utilized for the pectin extraction. So why we are not able to meet to that level? Why we are lacking behind? So the major difference between ours and the foreign strategy is, so the industry of lemon, the industry of oranges or industry of apple is completely centralized. And in case of us, we are not aware about the system and we are not having any centralized system for lemons. So for suppose today if I want any lemon, then easily it is readily available in the market. But in case of US, in case of Canada, it is hard to get the raw lemon from the market. They will, all the lemons or all the materials whichever they produce, they majorly process them and they will prepared in the bottle form. So that bottle will be available at the cheaper cost. So if you want to buy lemon juice, well, maybe 250 liters will come with, you can purchase with $1.5. But if you want raw lemon, it will cost only single lemon may cost $1. So here that is the difference. And with this, once they extract this juice and that is directly entering into the market, and which we are considering as waste. So if you throw this material, means this after extraction whichever remained material, if we throw them, then it will have the release of it will release the greenhouse gas into the atmosphere, because that will go under biodegradation. For suppose if you throw any food material like even lemon or orange peel outside, then it will start degrading, and after 1 week or 20 days, it will completely become water and black color. So means the black color indicates the complete neutralization of that particular biomass, right? So means during this biodegradation, it is going to release two gases majorly. If it goes anaerobic degradation, then it will release which gas? Under anaerobic degradation, methane will be the major portion along with CO2. If it goes for aerobic degradation, obviously CO2 entering into the atmosphere. So here whichever waste we are throwing into the atmosphere environment, that will create the greenhouse gas. Now they have the technology to process them, and they are trying to extract materials whichever which are readily available and which we are considered as waste. So because of this lacuna, they are having good production as well as good yield of the pectin, and they are at the stage to export to the other nations. So we are at importing stage currently. So here we have the potential, like the establishment of this industry may take longer duration or longer time period, but here at decentralized scale also it can be implemented and it can have the small scale industrial setup, like so where the bakery production to take place. So at the same scale we can have the pectin extraction and the same material can be utilized in the same food processing unit. So that's the main aim to start the research towards this pectin extraction. And if you see the applications of pectin, so it's going to start with pharmaceutical applications. So in pharmaceutical, while we produce these bulk drugs, so pharmaceutical industry also contains the formulation unit separately. So like pharmaceutical production will be taking at different stage levels. So at production stage, they will process the chemicals and they will produce the pharmaceutical suitable material which they want to produce. And at formulation stage, they will design these drug materials to deliver at the particular site where it has to deliver. So during this drug delivery system, this pectin is going to help as a absorbing material which can hold these pharmaceutical components for longer durations, and it will release slow release. So here two components, one is silica in amorphous form. So amorphous silica is also and at the same time, same way, pectin is also going to help us in the pharmaceutical industry, pharmaceutical formulation. So it's the major activity of pectin is it will hold the components are planning to deliver to the particular organ of our system. So that is the beauty of pectin in the pharmaceutical industry, major coating material. So here coating material as well as we can prepare this pectin into a thin film, and with this thin film, like if you coat different materials, so based on coating we can prepare this pectin as a selective membrane. So where it will allow only the selected components to pass through. So how this selective membrane will help us? So currently we are having different water treatment systems, right? So where we are getting from? So if I frankly ask about membrane technology, in India do we have any membrane technology which can indigenously process or indigenously can prepare? The unfortunate thing is we are not at a level to produce the membrane technology within our country with sophisticated nature. So we are depending on other nations. So where this pectin can play to have a selective membrane which will allow only the selective components to pass through. So by that way, and this is not the toxic component, and now we are using different polymer materials as a membrane material. So this polymer material, plastic materials will be entering into the water, so that is also going to cause nanoplastic which will directly to our body and it will enter into even our organs, right? So with the help of, like if we prepare those membrane materials coating with pectin, this is not going to create any harm to the body. So if it enters, then also it is going to give you the beneficial effect. Like it is also having antioxidant property. So it will absorb the cells which are getting generated in our body. So this antioxidation capacity will help us. So that is also beneficial. Like if we, like anyway when we eat jam, then it will benefit our body, right? Similar way, during this filtration material, so if it corrodes from the membrane, then it come out through the filtrate. So then also it is not going to have any negative impact. So that is one more application. And dairy products, so where different milk products, for thickening of milk products we can use as a, and bakery applications, and jelly applications where as I said, so depending on these pectin characteristics, so we are going to decide where we can use it. So if it is having like rapid jelliness or high gelling property, then we can process for jelly preparation. modify the characteristics of the pectin component. And as I said, it is also having antioxidant capacity. And one more recent advantage of this pectin has been identified, that it has a capability to even cure the ulcer cells in our stomach. So if any ulcers creates in our stomach, then this pectin has a capability to cure that. So but this pectin will be coated with or bounded with some other chemical component. So here they proven that calcium inner layers of the body. So even still we have so much of scope to identify its applications as well as even extraction. So if you see, still they are pending to work on. So anyone can, if anyone interested, so they can explore with this area. Last applications as well as the availability is also very much. So here the conventional method which we follow, we are giving as extraction, like where we can extract this material by following acid and heat treatment, where the pectin is going to converted into acidified. Under acidified and heat conditions, only this pectin component is going to detach from the cell wall, like where cellulose and lignin portion will be combinedly present here, like as are explained. Wall will be contain bricks, cement and plaster, right? So now we need to remove only plaster. We are not working on bricks and cement, right? So to remove this wall, here we are applying solvent, and it will detach from the bricks and cement, means cellulose and hemicellulose, and it will run out in the liquid form. And further the same liquid we are going to precipitate with the help of alcohol precipitation. Like ethanol will be utilized as a, in conventional method ethanol will be used as an precipitant, but here also we can explore, apart from ethanol, we can explore with the different solvent materials to precipitate it. So by that way we can reduce the cost of the extraction process. So likewise this is the conventional method where we can extract from the different food. Where in laboratory scale we have performed, and orange peels, we initiated with orange peels. So first we need to dry them and need to powder them, these powdered material. So here the main motto is to extract material or some volarized from the waste. So if we throw these peels, then it is directly entering into the environment and it will cause the greenhouse gas emissions. So here we are benefiting in two ways. One is we are reducing pollution, means the greenhouse emissions we are cutting down, and second thing, the same material we are converting as resource. So here we are having dual benefits. That and followed by heating, then this is the jelly pectin which we extracted. So and now you can see this is a jelly plain pectin, and this pectin having a beautiful character, you can mold this pectin into whatever you want to. If you want to convert into membrane, you can convert this. If you want to convert into tablet form, you can convert this into tablet or any gel beads or like powder even. So amorphous powder you can just this. So like whichever pectin we extracted, that can be converted into different molds as well as different forms. So that is means based on its characterization, we will be deciding where we can use this. Now we will discuss about the characteristics. So as I said, depending on characteristics of particular material, we will decide. For suppose when we come out from the 10th means C, then we will decide whether he will move towards social science or sciences or mathematics, depending on their interest, right? So that deciding factor is character. So in student case, we consider mark sheet of SSC. So based on his marks in social sciences, sciences will categorize, in mathematics will categorize, so he can capable of doing mathematics, so will send him to MPC, or like depending on that. So characteristics of the compound is going to decide. So here weight, these are the list of basic characteristics which will help for the like helping factor for deciding their applications. आगे क्या? So can we have 10 minutes break, then we'll continue.
Yeah, that's what. Yeah, perfect. So let's continue where water can do. Okay. In biofuel, many a time we think that water is not welcome, but if you think differently, water can do lot of chemistry. Okay. So what I was saying that if you go to higher temperature, it can be as good as hexane. Hexane is well known solvent for many non-polar compounds. Oil, hexane mixed well. Am I right? So do you know polar and non-polar compounds? Am I right? Do you know one saying is called like dissolves like? That's how you choose solvents. Am I right? If it is non-polar, then you will go for non-polar solvents. So if you have to clean oil, then you need some non-polar. All right? So like dissolves like. So what water is, you can make non-polar if you are here, and you can make water polar if you are here. Just tune it, temperature. So we keep talking green chemistry, this is green chemistry. You can use water the way you want to do chemistry. So here biomass is fully soluble. At room temperature you put, nothing happens, just some low temperature, but if you come here, it becomes like dissolved, become hexane. In fact, you can do combustion in water. You can light a fire in water. Can you think of? We use water to quench the fire, am I right? But in supercritical water, oxygen solubility is very high. So for fire, you need oxygen, and you can do that combustion. Supercritical water, oxidation process. Oxidation is combustion. So supercritical water oxidation, if you use, that process is used for highly toxic waste, where you want to get rid of that. You cannot put in landfill, you cannot treat in plant, it's so toxic and handling. You do supercritical water oxidation. Many military toxic ammunition and all which you invent, they use supercritical water oxidation. So high end of it, it's costly, but it has application for certain things. And supercritical water oxidation is combustion of material. So the product will be CO2 and water, everything gone. So using water, you can do whole lot of chemistry here. You can tune and it becomes green solvent. So advantage if you are using water, you don't have to dry biomass now, all right? You can use as it is. It's not dependent on type of biomass, it's algae, grass, wood, everything you can take in that. Reduced mass transfer, because water can penetrate very deeply, can be very mixed, so mass transfer limitation is less. I show you how you can make solid fuel green coal. Pyrolysis, you do carbonization, am I right, for make biochar. You can do pyrolysis to make char here, green coal, in presence of water. You can do liquid biocrude or bio oil, you can produce in presence of water. You can gasify in supercritical range, little higher temperature, you can make syngas, carbon monoxide, hydrogen and all. So water, what I am saying that is not always bad. Only thing you have to change the reactor, and reactor becomes high pressure now, because it works on pressure system. You have to pressurize, okay, and that's the challenge. If you have a pressurized reactor, that means you are putting lot of metals, right, thick reactor and all. So that's initial capital cost is high, but you are not dealing with corrosive chemicals now, so it's a trade-off. Especially in biomass, if you want to feed at high pressure, I said you, biomass transportation is a challenge. You pressurize, it turns into pellet. You put water, water will filter out. It may not move with water. All right, so you need some screw kind of reactor and other things. So that's a challenge. Salt, which was soluble at room temperature, it will heat at high temperature. So scaling another issue might come. So those are challenges, but it has very good applications. Technology have applications, but not uniform for everything. Pyrolysis is good for dry feedstock. This one is good for LG, where a lot of water or food waste. So one thing fits all is not the solution. You have to find which one is the best for what. I already talked about this. Dielectric constant goes down in supercritical, solubility very low, becomes fully miscible. Oil at low temperature, nothing, and then it mixes very well at a supercritical range. Diffusivity, viscosity, density all goes down. Diffusivity higher. So it's good for chemical reactions or any kind of reactions you do that. The question comes, you are putting a lot of energy now. I'm talking 300, 250, 350 degrees Celsius. So I'll bring you to some fundamental knowledge of thermodynamics. How many of you know latent heat of vaporization? So if you have water heating at 100 degree, it will be water for some time. Then you cross certain limit, then it will start fully vaporization. That's called latent heat of vaporization. That is required for phase change, liquid to gas. If you are working in subcritical water or supercritical, there is no phase change. All right, that's what we are and keep in liquid phase. So that heat of vaporization you saved. So energy which seeing looks like, yeah, it's higher, but I'll show you the number here. As an example, if you have a steam instead of subcritical water, its enthalpy is 2.2 per kg. 2.9 means that much energy you have to supply to have steam. But if you want to have not steam but pressurized water at temperature, subcritical water, the energy requirement is 1 megajoule per kg, 1/3. So we are thinking energy intensive. It's not energy intensive, it's pressure intensive. You have to have a high pressure system. Okay, but energy is not a big challenge. All three things you can do. We can make bio crude or bio oil. I'll show you. We have done a lot. You can do gasification. You can make syngas, methane. You can make it at higher temperature in presence of water. You carbonize and make a biochar or hydrochar. When we make in hydrothermal, we call it hydrochar, but it's basically similar to biochar. So I'll go to the application side of hydrothermal, where it fits better than other technology, is LG or high moisture content waste. So some idea about LG. How many of you already know or working in micro LG? So what is LG, micro LG? It grows very fast, right? If you have right amount of nutrients, light, it grows. In there. And it's uncontrolled bloom, it will cover everything. And we learn, can we control that, then we can grow LG. And why to grow LG? Because it will clean water. It will pick up nutrients from water. So if you have a wastewater, it will take up all nutrients from wastewater and it will grow. Why will we grow? One is cleaning, water treatment. Second is it's a biomass. Okay? And biomass without lignin. There is no lignin. Lignin, I was talking about kind of villain in last. It troubles a lot. Lignin chemistry and all those things interferes in fermentation and all. This one has no lignin. What it has is lipids, more oil. That's what we are looking for, make fuel out of it. What it has is lot of protein. And we need protein, am I right? High protein diet, we talk protein, animal feed, many other things. and it has carbohydrates. And all these things are easily accessible. It's not cell, it's just micron size kind of particle, am I right? Suspended. So the point is rapid growth. So if you are looking at photosynthesis efficiency in a very bigger picture, is biomass is better or is better? Land and do cultivation. Should I go for biomass? LG. At that it's kind of is much better biomass. In you can harvest this biomass versus LG is much higher than productivity is high. So efficiency, capturing sunlight efficiency is better. Okay. So rapid growth rate. Water, waste water you can grow, any kind of water you can grow basically. Saline water, fresh water, different species, more than maybe 50,000 species are known, even many more than, but it can grow. It does not require arable fertile land. Basically, it's a pond where you can grow. Okay, and the loss is only evaporation loss of water. Now, it requires CO2 air, so you can supply through air, but to improve the productivity, you can supply bubble air from flue gases. Biological sequestration, carbon sequestration basically. Biologically, you are sequestering. Direct air capture and biological sequestration going together here. All right. And utilization, CCUS, carbon capture and utilization. You can utilize this LG also. Biological capture is not enough, we talk. You have to do something with that. Here you can utilize. So all those good things coming here, and these are in demand. All three things are in demand. When you analyze LG, you will get these three major components. And if you like growing, cultivating, you can tune these numbers a bit depending on a species, changing nutrients conditions and all. You can play with that, lower protein, higher oil. There is a limit to that, but you can tune a bit. Okay, a species dependent, climate dependent where you are, but that's possible. The challenge is you have too many species. Which one to select? Good problem to have. Cultivation. Now farmers don't know how to cultivate LG. So you are looking for a new skill set. We are not talking house or aquarium level. We are talking big ponds to maintain. So you need to train people who knows how to grow LG. The closest one will be who fishery industry, aquaculture industry. They nutrients and have fish, healthy fish and all. So a skill set is required. Cultivation. Harvesting. If you take a bottle of LG, how you take LG out from water? Harvesting. How you concentrate it? Typical concentration in 1 milligram per liter, 2 milligram per liter, like that. So, no, 2 gram per liter, like that. So that's a very dilute. Still 1 gram, 2 gram in 1 liter is very less. Then how you process it, downstream processing, and nutrients. Now if you are looking at environmental engineering or environmental science and nutrients, can be pollution. If they picked up nutrients while cleaning the water, but if you don't do anything with nutrients, it will be released again. Am I right? So nutrients is fertilizer. So you want to grow LG, then you have to supply fertilizer. The fertilizer was coming from wastewater, some supplement you are giving, but if you don't recover, then fertilizer cost will increase. So nutrient cycling. Oil content is valuable. So this is open pond. We used to do in our university. This is from there, this picture. 1 acre open pond we had 10, 5, 6 years, and then we stopped. Look very green, but you harvest, you will get 600 milligrams. I said 1 gram is the best. 2 gram in photobioreactor. Open pond is 1 gram more common. So you are dealing with lot of water, and filtration is not a good choice to take it out. It's too much water, filtration, pressure and clogging. So how to harvest it? So coagulation, flocculation methods we use it. So that's why I said this for thermal. Let's not remove water, do chemistry in presence of water. So there are different algae, protein, carb, and they vary in that, and you which one you want. You can cultivate 2 different open pond or photobioreactors. If you go for open pond which I show outside, it's weather dependent, am I right? And have a certain control, you will control. It's people, but contamination is an issue, weather is. Grow here some design photoreactors, you can do closed conditions, light control. Want to do. Open pond scale up is easy, you can build big pond. Still challenging. Available, not downstream processing. Again, flexibility is low. If you want to control a strain in open pond, the local strains will take it up, right, over time. So bioreactor in open pond, you will lose water by evaporation. In photobioreactor, you have that control. So dewatering, even if this is dilute and looks fine, hydrothermal is very less amount, right? So you want to concentrate a bit to meet techno-economic. We are not dealing just water, some feed. So maybe 8-10% you want to concentrate. For that we do centrifugation, flocculation and all those things. So different options are there. Then once you concentrate it to 10%, and do hydrothermal process. And I showed you the graph, different temperature, different solvent properties, and you can play with those numbers between 200 to 600. You can make whatever you want, all these 3 things. So HTL has picked up a lot in recently. If you are following that, the hydrothermal liquefaction process is becoming more popular. Algae, sewage sludge, food waste, where you have lot of water. Hydrothermal liquefaction is like a simplified version pressure cooker. Still pressure than pressure cooker. You can put everything in a pressure cooking, heat and temperature, you get crude like bio oil. This crude is better than bio crude. Energy density is here is 32-33 megajoule per kg. If you remember pyrolysis oil, energy density is still 16-17 megajoule per kg. Okay, so this is typically done biocrude at 350 degrees Celsius, 320 degrees Celsius in that. In subcritical range, you don't go 400 because it has 320, 350, 300 is the good range for making biocrude using hydrothermal process. Now, if you compare with pyrolysis, that's there also you make oil. That oil has lower density, energy density, plus pyrolysis temperature is 450, 500. So you cut down 100 degree. So again trade-off. You are putting high pressure vessel but lower temperature. So economics. So any process development has to be integrated with TEA and LCA. And once you get biocrude, I said this is better crude than the pyrolysis oil. So it's easier. Again, you need hydrogenation process. You need to add hydrogen, but it gets and you can make it. Reliance has done a lot of work on this. They have pilot plant. They have collaborated a lot with United States National Labs. One time I was working with them, long time. So I have good insight at what they have been doing. They have big 10,000 pond, 45, we have invested at least for last 15 years a lot in this. And over the time, since it is good for wet feed stock, they look at sewage and food waste and many things they are testing in that based on this technology platform, because this crude suits them. If you get crude, it can go to their refinery, right? It's better than pyrolysis crude. So, biomass, wet biomass, this is a batch reactor, it can be continuous. Some you reduce severity of pressure, you get three things, bio oil or bio crude. Remember, you put water, so water has to come out. Water does not turn in oil, am I right? Water is called aqueous phase, it dissolve organic carbon, you can treat like a wastewater. A whole lot of nutrients will come here. So you can recycle for pond, or you can use for wastewater or many other applications. This is bio crude or bio oil. This is not biochar, it's solid residue, it is hydrochar. Same like biochar, but it has higher hydrogen carbon content than biochar, because it retains carbon in there. So it's more like coal, green coal. In Europe, some of the countries, many industries, they do green coal using hydrothermal process, hydrochar they call it. Another good point is you can make a lot of carbon material out of it. So it's a renewable carbon and it has many different applications. We have been working, my research group working on food waste, algae, and looking at carbon material we can do. We are looking at electrode material from this, from food waste. Using hydrothermal carbon, now we need to make it more graphitic, so we are looking at that, how to do that. I leave it, this one. Case study, you know more than me for India what's going on. Yeah, IT Madras has a lot of work on hydrothermal. IT Kharagpur also doing. IT Delhi, I collaborated with them, they are doing HTL. This is becoming more popular because of the water thing, a lot of water and better crude quality versus pyrolysis oil. Let me go to the next one. So, understanding carbon capture technology. Okay, this is the last session of this, and I want to make it more interactive because these are all repetitive things. From first I am looking how to capture carbon, and there are different technologies. The LG was carbon capture technology, am I right? Biologically captured. Sequesters also another thing. So there are many technology you can do, geological sequestration, biological sequestration and all those things. So let's make it more interactive. What is carbon capture? So you look for the sources where you get concentration of CO2. I think we talked about this post carbon pre. So I'm just trying to avoid no repetitions. Direct air capture. It came last 10 years, become more popular. So tell me, if you want to do capture growing algae, the concept started there is a flue gas. We should integrate algae cultivation next to or cement plant, where so it becomes CO2 supply, and then we can more. We can deal. than CO2. So productivity versus biology. These are not with the skill set of cultivation. All right, you are asking them, power plant, to grow algae next to you, and if you put boiler, they are happy. You are putting something else, they are happy, but asking them to grow algae, that was not going with the within the comfort zone, it was outside. So that's another challenge. But let's say power plant is 100 kilometers away from here, and if we grow algae here, atmosphere is 1. So soon struggling to put right there. All right. So you will see lot of studies cultivation next to power plant. Flue gases are not good. A lot of tons of study you will see that. Soon we realize it's a one world, right? One atmosphere. So move it where it fits better, where good land is there, good skill set is there, and you can do the same thing. So then came same concept is direct air capture. You don't have to capture right there. You can capture anywhere else. It's kind of offsetting. So direct air capture requires a large fan to draw air. You need large volume of air to pass. Remember 427 part per million of CO2. Okay? So you need large volume to handle such that you make some sense of it, impact of it. Otherwise, we flow high and then filter material, heat to release and capture CO2, and you can do that. So let me see. So here you can capture some chemicals. You can turn into carbonates or something, and then you heat, it comes out as a pure CO2. So that's a direct air capture. Storage, I talked, you can store once you capture, you can store.
Large fans and the filters.
Yeah.
So these filters are
Yeah, kind of membranes. Yeah, you can. Yeah, some membranes. Yeah. Yeah. Geological storage we already talked. Mineralization we already talked. Utilization we started talking. Enhanced oil recovery or EOR, what it is. So oil wells, when you drill it and take it out, over the time it depletes, slows down the production rate. Then we thought that there is CO2 coming from somewhere which we need to sequester. Why not oil wells? So we pump CO2 in oil wells. It's like just common saving pressurize. Using CO2, oil production goes higher for some time. You can draw more, putting pressure so oil will come out, and at the same time you sequester CO2. So oil company looked at positively in this process. So it's called EOR, enhanced oil recovery, and you sequester CO2. This is how it happened. Put reservoir, CO2 will push water, and then how it will come. So you can drain every bit of oil, which was difficult to after some time is more. So chemical absorption, amine as best solvent. There are different forms of amine, but they are the acceptable, available, employed. At absorption, definitely there is coming there. You can do membrane there, cryogenic there. We talked about that. Amines, adsorption, membrane, cryogenic. So if you compare chemical absorption efficiency, you can do very efficiently. It is high here, cost is moderate. be dealing with. That absorption is moderate, you have just some your so it's not moderate to high in the base. Membrane is moderate, low, moderate, cryogenic. Makes sense. But you can do that. Challenges, cost is the major challenge. We put industry to make electricity thermal power plant. They didn't plan at that time for capturing. There are 4 methods, why don't you use? And now they have to, that industry have to retrofit one of those, all right? So that's the cost. Storage capacity, how much can you store? Even if you are growing LG and if you are emitting more, an LG can take only so much, right? It has efficiency how much. If you are storing enhanced oil recovery, how much you can pump. Geologically, how much you can transport. Energy requirement in all those steps. Public perception. Challenge. So public perception, I will tell you one thing. How many of you know fracking, hydraulic fracturing? Have you heard about that? Fracking or hydraulic fracturing. So natural gas, we drill and it comes out, am I right? Or oil also, shale gas we call it, shale oil. So some of the deposits of oil or gases are such that it's very difficult to take it out. You can do vertical drilling, but it was difficult to do horizontal drilling. So the technology came up, now you can do horizontal drilling also. It's called hydraulic fracking, and now it releases oil where it was difficult to get before. It releases gas which was difficult to get before. Okay, fantastic. Many oil industry bloom. That's called shale gas. You Google it. Shale gas, fracking gas, things. United States, lot of Canada have lot on fracking and get it. In those areas, people started seeing water taps, some gas coming, they can fire it. Some study came up, is it causing more earthquake in this region because fracking you are doing, all right? So public perception came their picture. Is it a good to frack also? So those kind of thing comes up. If you sequestering, putting deep below aquifer, how water is getting in aquifer? Those kind of questions comes. There are many case studies. Tata is putting lot of effort in carbon here. Steel production, one of the carbon intensive, am I right? Reliance, I talked, they are putting a lot on carbon capture through LG. Or hydrogen, I talked hydrogen, what are they talking? And so IT Madras is working on CO2 to methanol. Adani Group, blue hydrogen plant, national policies. So I want to stop here and spend another 20 minutes on discussing about this. I have a lot to teach, but I want to start tomorrow, not a new topic. So what's your perception about LG? What do you think about LG to fuel? on LG to biofuel? Anyone? Yes. Are working. Working. Okay, for biofuel production. So how much lipid contents you are getting there?
Till now, like we get 25 to 30% in our algae, which is
That's very
naturally
good,
there,
yeah.
it is lipid content, but we are trying to ameliorate it using chemical physical methods.
Yes, but that's a good percentage here, 30%.
Actually, we have isolated it from our STP plant itself. So maximum we get 25%.
Yeah, that's why I'm saying you are in a good range then, yeah. And what you do with the oil? You just analyze and
Actually, right now we are just doing it on the laboratory scale, and our lab is also studying the synthetic ecology part, like the phycospheric bacteria, how they are ameliorating or helping the algae to survive, thrive, as well as increase the biofuel production. So my senior is working basically on synthetic ecology part, and I'm working on chemical ecology.
okay, yeah, that's good. So LD Judge,
Yes, sir.
many projects have shown that you can make jet fuel from those oil, am I right? And I don't remember the year, but 4 or 5 years back in Republic Day, there was a fly planes here. That was so that has a lot of potential and challenges also. I said it's very small amount in 1 liter, so how to do that? Wastewater treatment you can do, that's the big advantage of this. Any other thoughts on LG or any other thing? Yeah, go ahead. Go ahead.
To do one thing like during when the emissions are from factories, we can pass that flue gas through electrostatic precipitator, and then the heavy metals could like, like get onto one anode or cathode, and then after that we can pass that flue gas to this algae.
Yeah, that's what I was saying. So power plant, you take the flue and you can pass it, and that's what I was saying, that you can
But some
definitely
metals are also getting attracted to the electrostatic precipitator, so it is getting filtered out there only.
Yeah, you can use electrode to filtering out. Yeah, people have tried that, and that's a good idea.
Maybe that could be a bit costlier, so they are not using it.
Electricity is getting cheaper nowadays. The problem is electrodes, all right? But electricity supply is renewable electricity. So yeah, something to good idea. What else?
Strand which are can accumulate metals also, so you don't need to actually worry about so much for the activity.
Yeah.
There are already strands.
And secondly, there are also certain research suggests that CO2 improves fatty acid composition. So we have more saturated fatty acids than, so that will improve the biodiesel efficiency ultimately.
So let me go back. LG started with biodiesel. Okay, maybe 15-20 years back, waste cooking oil, biodiesel were picking up. Then we thought LG, it has oil, why not take oil, make biodiesel out of it. Okay. Yeah, so yeah, that was a Department of Energy, the program, LG Species Program, ASP or something like that. Department of Energy invested a lot, and they have a lesson learned, and they stopped the program for some time because it was not competitive, but it came back. Around early 2000, lot focus on ethanol. Then ethanol cellulosic challenges start coming. Then you went back to LG.
They want more carbon neutral, want to absorb this. So for that reason also has started.
Yeah, so the thing is biodiesel from LG. When I say biodiesel is a blend fuel, it's not raw. If you are growing LG and what you are saying is 30% oil, am I right? 25, 30%, that's one of the best. All right. In lab you can show 60%, but you cannot go high scale. Am I right? So best get you 20, 30, 33%. What you do with 70% of rest of the material? So if you are making biodiesel, you are taking only 30% of oil and also triglyceride on that will make biodiesel, not all lipids. So soon we realize that what we are just focusing on triglyceride making biodiesel and we are wasting lot of residual biomass. So then started coming concept, why not entire biomass for fuel? So hydrothermal liquefaction, turn everything, oil is definitely there, then carbs and proteins also put everything, you get crude and then clean it up and make jet fuel. So that was IIP Republic Day demonstration that hydrothermally you can make these things. So biodiesel moved away, now we are looking at drop-in fuel from LG, where you can convert everything. Or why not take proteins out? Protein can be a good animal feed, fish feed and many other things, and then focus oil on for oil. So the biodiesel kind of faded away, LG, it has started and we saw a lot of benefits than just biodiesel. There are many high value
integrations
yeah.
possible. For example, we can make it pigment centric. We have more pigments, for example, phycocyanin or
Phycocyanin. I have those.
I
I am studies on that. I'll show you tomorrow. It's a carotenoid. You can get it out. Pufa. You can get out. Omega 3 is a good source. You can get it out from LG. So it has lot more potential than we can tap. Okay, so that's why it's picked up. Now, how many you heard about macro LG, not micro? You know, okay. So macro LG. Seaweeds basically, right? Seaweeds are macro LG. And that is getting attention a lot now for fuel purpose. So difference between micro LG and macro LG is macro has more carbohydrate, very low amount of oil. So you are looking for carb there. High-end food are seaweeds, am I right? Seaweeds very high value for food, but there are
also
certain
have high polyunsaturated fatty acids.
yeah, fatty acids, yeah.
And then there is also possibility to make kappa safe and some other agriculture fertilizers, liquid fertilizers.
Liquid fertilizers. So,
Sir, I need your suggestion. Whenever we use flue gas as a feed, CO2 feed to the algae system, so along with CO2, it also contains SOx and NOx part. So it will acidify the system. So by that way, algae will not sustain for longer durations if we continuously pass on flue gases. Then how we can sustain the system by favoring the growth of algae? Because it will become acidified when we continuously pass on SO2 and NOx gases.
Actually, I can answer this question.
We have tried actually multiple strategies to get rid of this problem. One thing is that we can adjust with the NOH on certain points of time when that is becoming acidic. One another thing is that we can actually have a CO2 injection intermittently. So when we will inject the CO2, it will become acidic, but it will be a slow dose. So algae will take up and will release OH minus. Again, pH will be balanced. So in that way, that can be tackled. Yes. And many people are integrating two ways. For example, they are using NOH. First, they will make sodium bicarbonate and then they pass sodium bicarbonate in the medium. So CO2 will not be immediately released and will be taken up by the microalgae.
so macro LG. So macroalgae is gaining attention because of few benefits. One is you don't have to harvest like algae. You just scoop it out. Am I right? There's a lot of cost saved there. Harvesting is a big challenge which you did that. Then you can grow somewhere which you don't, even the sea and saline water you can do. So these are the benefits coming. So it's kind of we learn something, then we move to other, then we think this was better. So it's kind of back and forth. And right now in last few years, macroalgae is getting more attention over the macroalgae because of these reasons. Okay. Any other question? Okay, let me change the topic. Yeah, go ahead.
So in the earlier before lunch we were talking about heating values of different things, and we were talking why blending is not preferred because the efficiency is reduced. But we were also talking about increasing the efficiency of biodiesel. So can't there be there must be methods now which by which the diesel or the fuel produced by biomass, its heating value is increased, like hydrogenation is done to them, and then after that if the blending is done.
Yeah, so if you do hydrogenation process, this is drop-in, so you don't have to do blending. It's ready. Drop-in means ready. Go to gas station, you have a biofuel which is ready to be 100%, so you don't have to blend. Blending started with biodiesel or bioethanol, which was made from first generation food or vegetable and all. And the heating value was one of the reason. You have oxygen, and you saw the chart. Oxygen reduces heating value. Biodiesel, if you write formula, ether, fatty acid, ethyl ester. So it has an oxygen bond there. So it will, oxygen is not always bad, but it's just little amount for the clean, not more than that. Ethanol has lower heating value because of oxygen there, but little oxygen is fine. But it's a blending, that's why it's a blend fuel, not 100%. Okay, so composting. All composting, all right? Biochar, you know. So what composting does, what biochar does, which one is better in terms of carbon sequestration, you tell me. If you don't do anything with organic material, it will degrade and it will emit greenhouse gases, methane and all. If you are doing composting, you are reducing the degradation, am I right? And capturing carbon, making good for plants also, nutrients are there, microbes can thrive and all. But how stable that carbon is? How long it will last? If you are thinking not for gardening, thinking for carbon sequestration, what would be the stability of compost versus biochar? So biochar will be more stable because it's more carbonized, while compost is less stable. We keep changing that, so it will degrade over, partially degradable. So when we talk about yeah, slowly release, yeah. So one thing we are working is biochar land application. And biochar, tomorrow we'll be talking, but as it has been shown that it retains water because of its porosity. So it's good for plants. It retains nutrients. So one of the challenges in normal agriculture system is you put lot of fertilizer, rain, irrigation goes drain. So if you put 100, only 10 is useful, 19 goes here and there, and that causes pollution and many other things. Okay? So drip irrigation came. It will be efficient. If you are putting biochar, it has shown that it will retain water for longer time, nutrient for longer time. So your efficiency gets better. Okay, now we are thinking that can biochar be a fertilizer kind of thing? Can we incorporate NPK in it? Then it can be a fertilizer and carbon sequestration all together. So if you are thinking like that, that's another direction. Just applying in land as a biochar, can we replace fertilizer, supply slow release NPK through biochar as a carrier? So that might address few things. Yeah. Slow release, we are talking, how can we design a slow release? Yeah, so slow release works very well with pharmaceutical industries. With all tablets we take designed for slow release, gel and all, it takes 12 hours. Tell farmers, they are looking for low cost something and tons of material. And if you start encapsulating, we are adding lot of cost to that. All right? So that's the one issue will come up. At a small scale is fantastic, but if you design that, that's one. But it's not, there may be a better solution to reduce the cost. But that's a good idea, slow release, how we can do that.
Sir, biochar or bio-based material can be used as like filters or sorbent in DAC, like direct air capture.
Yeah, filter. So
It can be used.
yeah, tomorrow I'll show on biochar how we try to use for filter. I think this morning I was talking about lead removal using biochar as a filter.
So can it help in air purification or something like that? Air pollutants removal or?
Yeah, it does. So wait for tomorrow. If you
Okay,
are here,
okay.
I have a full lecture on that.
Okay, sir.
So that's thing. Land application of biochar, if you are doing that, I'll tell you one practical. How many of you have seen biochar? You have seen that, okay? How it looks? Is powder, fluffy, very low density. Yeah. So if you leave it here at fan, it will fly. Am I right? And we are talking about it can be applied in land. You can blend with soil and put it, and that's good for that. If you are applying biochar in land just like that, what will happen? Wind will take it away and you will create air pollution and all those things. And even if that don't happen, the person who is putting biochar will have to have a mask or something. Am I right? Yeah, so it does all good things in lab. When it comes to transition to field, I'm bringing all these problems. All right? So one of the target area we are doing, my PhD student is working on that. Can we pelletize or granulate? And then you spray like a fertilizer. Right? If you can do that, then it solves engineering problem, handling problem, pollution problem. All right? Application easily you can do. You can put machines now to spread it instead of doing hand. So those are the practical transition things. So we do some chemistry in lab, then how to transition, and then we realize this is the address to be done. And I'm talking one step ahead. When we spread it, can it be fertilizer also? When we granulate, can we add some NPK in granulation? So it does fertilizer plus water retention and filtration and other things. So yeah, that's another good area of study. Anything else? Yeah.
Glucose, everything gives a different kind of fuel with different procedures we use. But my question is, like, galactose and glucose have almost similar structure. They all are sugars, and at the end, why the same procedure doesn't give the same kind of fuel? Why we are getting hydrogen with galactose but not with the glucose, and we are getting ethanol with glucose and cellulose?
You are talking biochemical or?
No,
thermal?
I'm talking about like every procedure. like when I was reading about galactose, which we usually get from red alga, so it is rich in galactose. But when we do the procedure for biofuel production, we get hydrogen more easily as compared to biocrude oil and all. So why the same procedure doesn't give the same kind of fuel with all the monomers and
So
polymers?
biochemically, if you are talking, I'll go on both sides, thermal and bio. Biochemically, what you're talking, then it's more on what microorganisms, their metabolic pathway like. Am I right? So they will follow that path. So certain products are majority products, and there will be byproducts, the parallel products. So that's how what glucose Baker Street will take you to ethanol. Some other things will take you to more lactic acid. Okay, so this is how metabolic pathway, biological side. If you are looking at thermally, then you are looking at elemental energy, carbon, hydrogen, H by C ratio and all. Higher the ratio, more hydrogen you will get. Okay. All right? So let's say you have methane and glucose. Where you will get more hydrogen?
Methane.
Methane, because you have higher the hydrogen ratio. So different kind of sugar will have a different H by C ratio, percentage wise. So you will see difference in production and different things. Okay, but if you are producing same fuel with 3 different compounds, the yield will differ. Product may not differ in thermal way. Okay.
Okay, thank you.
This difference also exists when there is a kind of we are using this glucose and galactose for heterotrophic growth of microalgae. Then also we observed certain differences in the fatty acid composition. That means the both are not behaving the same. Even biochemically they are digested inside the cell.
Yeah.
So even they have similar structure. They have something to do with this
Biological, metabolic
biological,
pathway, that's what
because
I'm saying.
they give very different result when we use it heterotropically.
Yes, that's more on the metabolic side. Where
Yes,
they
yes,
like.
yes.
Yeah, that's what I'm saying.
So the similar thing maybe here in the chemical mixture also.
Yeah, okay.
It's possible.
We are almost out of time, so go ahead with one question or so. Anyone? So paper industry, let me give you this anecdote and then we'll stop. Have you seen paper industry visited? Yes. What they do? Just where do they get feedstock? Feedstock means wood. So where that wood chips comes from? Timbers. Where? Nature. Where is nature? It's a forest somewhere. Am I right? They cut and bring it to a plant. So I visited one forest like that. Okay, I will not name the paper plant, but they used to get logs from forest. And we got chance to visit that, how they log it and what do they. So what was being done there, cut the log because that's what we want. Leave everything on the forest. Okay, twigs, leaves, everything, put it there, logs gone. And then there will be another cheaper will come because you are supposed to clear the pathway also. You cannot leave just like that. You need to log next stage, so your machine need to move. So you will remove those residue and put in a cheaper, put in a truck and it will go. So we logs going for paper making and all the chips and leaves and all which are put in the truckload going for boiler mixed with dust and many other things. And we were interacting and say that basically we are taking half of water. No, that is black liquor, that is different. Once you got the log out, this is tree, you got this part, the leaves, twigs, stems, you leave it there. Yeah, debarking and all. So those materials at the forest site were left like that. So they will be chipped, loaded in a truck, go to the factory, run the boiler. But what we are discussing, what you are taking here to there, half is water. If it was a fresh tree, moisture is high, you are chipping and transporting, taking to a boiler, but it's 40–50% moisture you are taking. All right? Can you be more efficient, get torrefied or charred or carbonized, and then you transport it? Then instead of 4 trucks, you are needing 1 truck or 2 trucks. Okay, so that's how you can efficiency improve it. So, things are being done which can be improved in many different ways. Now the thing will come that making biochar at the site is possible or not, economically feasible or not. But this is an idea which can be tried. Okay. Okay, so we are out of time and enjoyed and looking forward to continue our discussion tomorrow. Okay? Well, good night. Thank you.
The session is not over yet. You can please please be seated at your places.
How we can decide the characteristic of compound. So as we discussed about pectin, so just we'll have small demonstration with 2 experiments, and they are also short experiments. It will not take much time, but it will decide that can be utilized for which purpose. So within short experiment, like it doesn't require any sophisticated instrument or sophisticated technology setups. So with the short experiment, we can decide. For suppose in case of silica, to decide whether it is amorphous or crystalline, we need to go for instrumental analysis. So XRD